Okay, let's unpack this. We talk constantly about the relentless, almost theological scaling of AI. You know, trillions of parameters, massive compute.
Yeah, the prevailing wisdom that bigger is always better for large language models. Smarter, more capable.
Exactly. And look, for tasks like just general conversation or creative writing,
Yeah,
summarizing huge texts, it holds true. Scaling works there.
it does. But then you hit this like profound structural wall.
Mm-hmm.
You give these colossal trillion parameter LLMs these very specific structured reasoning tasks, things that need absolute internal consistency.
That's Sudoku.
Sudoku, exactly. Or navigating a really complex, say, 30 by 30 maze,
Yeah.
or tackling those infamous ARC-AGI geometric puzzles.
Ah, the abstract reasoning ones.
Right, the ones commanding abstract conceptual logic. And suddenly, those brute force models, they just start to fail.
It's not because they lack knowledge, right? It's something fundamental about how they reason.
Precisely. Their reasoning structure is fundamentally fragile for these kinds of problems.
Yeah. Right. Even top models, like Gemini 2.5 Pro, despite all the compute thrown at them, they still struggle to get anywhere near human-level accuracy on these, well, symbolic logic tasks.
And our core source material today really hammers home the main reason for this failure. It's the autoregressive generation.
Okay, explain that a bit more.
Well, an LLM generates its output token by token.
Mm.
One word, one number after another, sequentially.
Right.
So imagine it's solving a Sudoku. If step 5 in a sequence of maybe 50 steps is wrong, let's say it puts a 7 in the wrong cell,
Okay.
then all the remaining steps are built on that faulty premise.
Yeah.
The entire 50-step answer just becomes invalid.
Ah, I see. The error cascades and the whole thing collapses logically.
Exactly, it's fragile.
So our mission today for this deep dive is to explore a really counterintuitive solution proposed in some recent research. Basically, the mantra that sometimes, for this kind of hard reasoning, less is more.
It sounds completely backwards compared to the scaling narrative, doesn't it?
It really does. We're looking at a path towards potentially superior structured reasoning using models that are, well, utterly tiny compared to LLMs.
So we need to formalize and really understand the initial, quite complex attempt at this. That's the hierarchical reasoning model, or HRM.
Right. And then contrast it with its successor, which is this incredibly simplified, super efficient model called the tiny recursion model, or TRM.
Okay.
And here is the fact that should, I think, anchor this entire deep dive for you, the listener. TRM uses an absolutely absurd fraction of the parameters.
How small are we talking?
We're talking maybe 7 million parameters. Compare that to 27 million for the original HRM.
Still tiny compared to LLM.
Exactly, or hundreds of billions, even trillions for models like DeepSeek R1 or, Grok 4. It's minuscule.
Wow.
Yet, on these hard puzzle benchmarks like Sudoku-Extreme, TRM achieves significantly better generalization. It hits 87.4% accuracy.
These big LLMs.
Many of them just score 0.0%. They can't reliably solve them at all.
So what's truly fascinating here, I think, is that this isn't just about making smaller models run faster or cheaper. It's about a fundamentally different reasoning structure.
A different way of thinking.
Kind of, yeah. We're shifting away from that statistical brute force of just predicting the next token to a structured, iterative refinement process, a process defined by deep recursion.
Recursion, meaning the model kind of calls itself or applies its logic repeatedly.
In essence, yes. And this structure bypasses those inherent limitations of standard autoregressive generation. And crucially, it avoids making some, well, questionable mathematical assumptions that plagued the earlier attempt, the HRM model.
Okay, so we really need to formalize this. Define the mathematics behind this tiny network recursion, paying super close attention to how the gradients, the learning signals, are tracked.
That's the key, the gradient flow.
How can a model with less than, 0.01% of the parameters of a giant LLM beat it so soundly on hard reasoning? Let's start by digging into those LLM shortcomings and that initial complex solution proposed by HRM.
Okay, so as we established, the primary headache with large language models in these structured tasks is that inherent autoregressive fragility.
Right, the domino effect of errors.
Exactly. They predict a sequence, and sequence errors just cascade catastrophically in problems that demand internal global consistency, like finishing a Sudoku puzzle correctly.
And researchers have naturally tried really hard to mitigate this, but within the existing LLM paradigm, right?
Yeah, they tried to patch it up. The most famous attempt is probably chain of thoughts, or COTI.
COTI, that's where you prompt the model to think step by step.
Exactly. You give it examples of step-by-step reasoning, trying to force the LLM to write out its internal logic before it spits out the final answer.
Does it work?
It helps for some tasks, definitely, but it's still quite brittle. First, you need really high-quality, often expensive reasoning data to train it effectively.
Okay.
And even then, the reasoning trace the model generates might look plausible, but be logically flawed somewhere inside, leading to the wrong conclusion anyway.
Ah, so it can fail silently in a way.
Precisely. Plus, it significantly increases the computational cost because you're generating a much longer sequence. And you're still stuck with that fundamental token-by-token generation method. It doesn't fix the underlying fragility.
Okay, so COTI isn't a silver bullet. What else?
Well, another technique is test-time compute, or TTC.
TTC.
This tries to overcome the fragility by basically sampling multiple potential answers. Say you get the LLM to generate 100 different possible Sudoku solutions.
Okay, like a brute force check.
Kind of. And then you report the one that appears most frequently, or maybe the one the model itself rates with the highest confidence score.
Right, find the consensus answer.
Yeah. And TTC does improve reliability, sometimes significantly. But it's a very expensive Band-Aid, isn't it? It's not a structural fix for the reasoning process itself.
Makes sense. You're just papering over the cracks with more compute.
Exactly. And the limits of TTC become really evident when you look at the cutting-edge benchmarks. The source material we're looking at cites the ARC AGI-2 challenge.
That's considered a really tough test, right? Frontier AI reasoning.
It's extremely tough. Abstract visual reasoning. And even the highly computed Gemini 2.5 Pro, using intensive TTC methods, only manages about 4.9% test accuracy on that benchmark.
Wow, less than 5%. That really shows the limitation.
It does. The core structure just isn't suited for that kind of deep, iterative refinement or self-correction needed for complex logic puzzles.
Which brings us to why the hierarchical reasoning model, HRM, was proposed as a different path, right? By Wang and colleagues in 2025.
Exactly. Instead of trying to fix autoregressive generation, HRM uses supervised learning.
Okay, so it's trained specifically to produce a correct output for a given input problem, like a classifier.
More or less, yes. Its goal was to tackle that fragility head-on by introducing two main structural novelties.
What were they?
First, this idea of recursive hierarchical reasoning, and second, something called deep supervision.
And the original HRM model itself, parameter-wise, was it big?
No, relatively small even then, around 27 million parameters. And it was trained on quite modest amounts of data, maybe about 1,000 examples per task.
Which is tiny compared to the pre-training corpora for LLMs.
Absolutely minuscule.
So HRM had this biological inspiration. You mentioned high and low frequencies.
Yeah, the original paper talked about mimicking how the brain might handle temporal information, using different neural components for high-frequency, short-term processing, and other components for lower-frequency, longer-term abstraction.
Interesting. Does that biological analogy hold up?
Well, as we'll see when we transition to the tiny recursion model, TRM, the researchers later found that maybe the biological analogy wasn't strictly necessary.
Ah.
The real power seemed to lie more in the deep, iterative improvement across multiple training steps, which they called deep supervision. The structure worked, maybe just not for the originally stated biological reasons. Hashtag tag 1.2 rigorous definition of HRM structure and components.
Okay, so now we really need to get into the weeds. We need to formalize the architecture of HRM. Because the simplification that TRM introduces only really makes sense if we understand the complexity it's stripping away.
Right. HRM is built on 4 core learnable components.
Yeah.
Think of them as 4 distinct functions, each parameterized by its own set of weights, its own theta.
Okay, component 1.
Let's start with the input. You take the raw input problem, which we denote as tilde.
So for Sudoku, that's the 9x9 grid with the initial numbers and empty cells.
Exactly. The first component is the input embedding function. Let's call it $5. Its job, parameterized by theta, is to convert that raw input tilde into an embedded input, which we'll call $6.
And the purpose of this embedding step is pretty standard for neural nets, right? Turning discrete things like numbers or grid positions into continuous vectors.
Precisely. You're turning the raw data into a dense, continuous vector space where arithmetic operations inside the network become meaningful.
And what does this embedded input $6 look like dimensionally?
Typically, it takes the shape of allele, where the batch NOS is the batch size, how many problems you process at once. Dollars is the context length.
So for a 9x9 Sudoku would be 81.1.
Exactly, 81 positions. And dlar is the embedding dimension, the size of the vector representing each position.
Okay, so that's $5. What are the next components? These are the recurrent ones.
Yes. Next are the 2 networks that do the heavy lifting, the core recursive reasoning. There's the Low-level recurrent network, 5LR parameterized by a theta, and the high-level recurrent network, 5LR, with its parameters, the etstat.
Low level and high level.
5LR dividers, what do they work on?
They produce and consume their own respective latent features. 5LR works with dollars, which you can think of as the detailed reasoning feature, and 5LR works with TLRs conceived as the more abstract, perhaps solution-related feature.
Got it. Theta for low-level reasoning, theta for high-level abstraction, and the fourth component.
Finally, you have the output head. A TLR is parameterized by theta. This takes the finalized high-level latent feature after all the reasoning steps and projects it back into the format of the desired output. We call the predicted output 5R. Okay, so 5 hours encodes, 5 hours in reason recursively, and 4 hours decodes. But you said 5 hours aren't simple layers.
No, definitely not. It's vital to understand that 5LR are themselves quite complex. Each one is a 4-layer transformer architecture.
Wow, okay. So each reasoning step involves passing through a multi-layer transformer.
Correct. And they utilize modern components you see in state-of-the-art models, designed for stability and efficiency.
Like what?
They use RMS norm for layer normalization, that's often preferred over standard layer norm these days, for efficiency and stability reasons.
Okay.
They operate without bias terms in their linear layers, which is a common design choice in many recent large models. They use rotary embeddings, ROPE, for injecting positional information, which is very effective.
ROPE.
And they employ the cs.LG activation function. That's been shown to be superior to the standard ReLU activation in many deep learning contexts. So these are not trivial components.
Okay, so sophisticated building blocks. Now let's get to the core mechanism, that recursive hierarchical reasoning. How does a single forward pass actually work? The paper uses 1-232 low-level steps and 232 cycles of recursion as standard.
Yes, let's walk through that standard setup. A single forward pass is a sequence of 6 distinct function evaluations.
6 steps. Okay, step 1.
Step 1 is just the initial embedding we discussed. $1, quad X left arrow, FI, you get your embedded input, 6 Ls.
Makes sense.
Next come the first 2 steps of the low-level reasoning. This is framed as the high-frequency work, where the model processes the combined state of its current latent features, 702 solars, and the static input, 6S.
So it updates the low-level state, what, twice?
Yes, sequentially, $2. Quad ZL left arrow, FL, ZL plus EH plus XL. Notice it uses the output of step 2 as the input cell for step 3.
Okay, 2 passes through the low-level transformer them. Now here's a crucial point from the outline. These steps are run without gradients.
Exactly. In the original HRM formulation, these first 2 Feisal computations are done essentially in a no-grad context. Any changes they might implicitly suggest for the wave cycle are not tracked for backpropagation later, they just update the state.
Okay, that seems important. What's step 4?
Step 4 completes the first cycle of recursion, so TT dollars is done. This is the low-frequency, high-level update intended to abstract the current state, perhaps consolidating the reasoning from settled dollars into the solution state, $4, quad ZH left arrow FH, ZL plus CH. It takes the output pseudo from step 3 and the previous pseudo and passes them through the high-level transformer, $4.
And this step 4 also run without gradients.
Correct. Also without gradients. So we've completed 1 full cycle, 2 low-level, 1 high-level, and so far, none of this computation has contributed anything that can be used to calculate a loss or update the model's weights. It's all just state refinement.
Okay. This feels a bit strange. Where does the learning happen? This brings us to the complex part, the fixed point approximation steps.
Exactly. Now we hit the heart of HRM's complexity and, arguably, its main weakness. Before proceeding to the steps that will track gradients, the latent features are explicitly detached from the computation graph.
Detached? You mean like calling .detach on the tensors in PyTorch?
Precisely that. You'd literally write something like ZL vels left arrow, ZL welt arrows, Abro left arrow, ZL CL.
And what does that do?
It cuts the connection. It tells the automatic differentiation system, forget where these values came from, treat them as constants from this point forward. This is the crucial physical act in the code that enforces the implicit function theorem approximation we'll discuss soon. It literally severs the gradient flow from those first 4 steps.
Wow, okay. So it deliberately throws away the history of how CLLPSS got to their current state before doing the learning steps.
Correct. Now, the remaining steps, 5 and 6, are the final function applications in this forward pass. And these are tracked with gradients. These are the only parts of this whole 6-step sequence that will actually contribute to the loss function and allow the model weights Fields to be updated.
Okay, so what are steps 5 and 6? Another round of $5 as
Yes,
well.
exactly. $5,
Yeah.
quad ZL left arrow FL, ZL plus ZH plus X, quad text with gradient $6, quad ZH left arrow FH, ZL plus ZH. These look identical to steps 3 and 4, but now the gradient tracking is turned on.
Okay. And then the final prediction comes from this last $1.
Yes. The output head computes the final prediction, usually by taking the argmax over the logits produced by vidwars.
Yeah. So to summarize HRM's forward pass, it's this complex dance. 6 internal steps, 4 are run detached, just for refining the state $0 and dollars. Then you cut the history. Then you run the last 2 steps with gradients, and only those 2 influence the learning.
That's the essence of it. A pretty intricate machine involving 2 separate transformer networks and this very specific gradient handling based on that detachment step. Hashtag tag 1.3 deep supervision and the IFT rationale, the math justification.
Okay, that forward pass seems complex, maybe even a bit counterintuitive with the detached gradients, but you mentioned another key HRM concept, deep supervision. This was how it achieved high effective depth.
Exactly. Deep supervision is the mechanism designed to allow the model to reason iteratively over many, many passes during the training process, far exceeding the computational depth of just one of those 6-step forward passes we just described.
How does it work?
It's actually quite simple conceptually. Deep supervision works by reusing the latent features, ziggies and dollars and saddies, from the end of the previous optimization step as the initial state for the next optimization step.
So the sags that come out of step 6 in one training iteration become the starting ziles for step 2 in the next training iteration.
Precisely. This creates a temporal connection across training batches or steps. It allows the model to iteratively refine its internal state and therefore its potential solution over many consecutive updates. The HRM paper explored reasoning over up to 16 plus 6 such supervision steps.
Okay, let's think about the sheer computational depth this implies. If HRM used, say, 4 layers per network, 4 elevator fake ran 1 LS2 low-level steps per cycle, 2D2 cycles per forward pass, and then did this for 1 less of 16 subtle supervision steps, how deep is that, effectively?
Let's calculate it. Each forward pass involves 1 NO2 calls to fossil and the T2 calls to 4. Wait, the outline says the sequence is 4 LFH, FH, FH, 4 lives. That's 1 O with 3 calls to follow and T2 calls to 4 LO pass, tracked across deep supervision. No, wait, the 6 steps were 1 of 50, 4 left to 3 post to 4 Os, 4 LO 6, 4 less than 6 fos send, so that's 3 calls to followers, so that's 2 goals. And 2 calls to 4 layers, sips, and each is 4 layers deep. So 1 forward pass is $3, 4 plus 2 times 4 plus 8 is 22 layers traversed.
Okay, 20 layers per forward pass. And if deep supervision connects 16 queues of these passes,
then the model effectively reasons over $20 times 16 equals 320 whole layers of computation across time. That's how it gains its reasoning power through this iterative refinement over time, enabled by deep supervision, not just by stacking layers vertically in one pass.
320 layers of effective depth from a model with only 4 actual layers in its core networks. That's significant.
It is. But now we had to hit the mathematical justification, or perhaps the mathematical rationalization, for why they only tracked gradients through those last 2 steps, 5 and 6 of the forward pass.
Right, the detachment before step 5 seemed very deliberate. Why do that?
This decision was primarily driven by trying to apply the implicit function theorem, IFT, combined with a technique called the one-step gradient approximation, which comes from work on deep equilibrium models, DEQs.
Okay, implicit function theorem, DDQs, sounds heavy. What's the core idea?
The core idea, in this context, is that if you have a recurrent function that eventually converges to a fixed point, meaning a stable state double where we're running the function one more time doesn't change the output, calls in the LZ, then theoretically, you don't need to backpropagate through the entire history of getting to that fixed point.
Why not?
The IFT provides a way to calculate the gradient at the fixed point using only information from that final step. So you could approximate the true gradient by just tracking that very last step of the computation, assuming you're close enough to the fixed point.
So it's a memory optimization trick. Avoid storing the whole computation graph.
Exactly. Backpropagation through time, EBTT, for very long sequences is notoriously memory hungry. This IFT one-step approximation offers a potential shortcut.
So mathematically, what does this fixed point condition look like for HRM's OLISH and Z$, in the Z age?
A fixed point would imply that the latent features have stabilized. So I delta prox FL, ZL plus ZH plus X.
C Tyler proxys FH, ZL plus ZH dollars. If these equations approximately hold true, the theorem suggests you can get away with just tracking the gradient through the final application of 5HC, steps 5 and 6. And it should be a decent approximation of the true gradient needed for learning.
Okay, so it sounds mathematically convenient if the assumption holds.
Big if.
And this is where, as you said, it gets really interesting because the follow-up TRM research critically examines this very assumption. They argue the fixed point assumption was tenuous, maybe even invalid in the way HRM actually used it.
Precisely. Here's the crux. A true deep equilibrium model, a DEQ, would typically iterate the function $5 until it actually solves for that fixed $0.7. It would check if the difference between Villard's step color and step tip TRLR is very close to zero.
Right. It would confirm convergence.
Yes. But HRM did not do this. It didn't iterate until convergence. It just ran a fixed number of steps, those first 4 steps, LFL, FH2I, without gradients, then detached, then ran 2 more steps with gradients. It essentially assumed that after those first 4 steps, the state was close enough to a fixed point to justify applying the one-step gradient approximation via detachment.
So it wasn't actually checking if the fixed point condition was met.
No, and this wasn't just a minor theoretical oversight. It meant the entire mathematical foundation HRM was supposedly built upon was shaky in practice.
Is there evidence for that shakiness?
Yes, the TRM paper, which builds on HRM, specifically points to evidence, including figures in the HRM paper itself, showing that even when they experimented with higher numbers of recursive steps, like un7,7, t equals 7,7, the residuals for both $0 and especially $7 were often still significantly far from zero at the point where the gradient detachment and approximation were applied.
So the system was clearly still changing, still dynamic, not converged.
Exactly. If the residual is clearly greater than zero, the system hasn't stabilized. It hasn't reached that equilibrium, that fixed point.
And if it hasn't reached the fixed point?
Then the mathematical justification for using the IFT and the one-step gradient approximation falls apart. Cutting off the gradient history after just 4 steps means you are essentially learning based on an incomplete, still evolving target state.
So the conclusion drawn by the later TRM researchers is stark. Convergence to the necessary fixed point was highly unlikely in the HRM setup.
Yes. Which implies the IFT justification was insufficient, and that enforced detachment, that severing of the gradient flow, was likely harming the model's ability to learn the full, true reasoning path required to solve the problem. It was optimizing for memory at the cost of theoretical soundness and potentially performance. Hashtag 1.4 adaptive computational time, ACT, and it's called.
Okay, so we have this complex HRM model with deep supervision allowing up to 16 iterations. But based on a shaky mathematical premise for its gradients, how did they manage the training cost of potentially running 16 full forward passes per sample? That sounds computationally brutal.
It would be. And that's where the third key component of HRM comes in. Adaptive computational time, or ACT.
ACT, adaptive time.
Yeah, the idea is if every single training sample always used the maximum null 1600 assignment steps allowed by deep supervision, training would indeed be prohibitively slow, especially with limited data.
So ACT is about efficiency, making it faster.
Exactly. Its purpose is efficiency. It uses a learned halting mechanism. The model essentially learns to decide at each step of the deep supervision process whether it's confident enough in its current answer to stop refining and move on, or if it should continue for another step.
So it can bail out early if it thinks it's already got the right answer.
Precisely. And the HRM authors showed this was quite effective in practice. They managed to reduce the average number of supervision steps needed per sample to less than 2 on datasets like Sudoku-Extreme, instead of always running the full 16.
Less than 2 steps on average, down from a max of 16. That's a huge saving. So ACT made HRM training practical.
It made it more practical, yes. But there was a hidden cost.
Wait, if ACT drastically reduced the average number of steps, how could it have a hidden cost? The outline mentions that the ACT implementation effectively doubled the computational cost of each individual optimization step. That seems contradictory.
It does seem contradictory at first glance, but the hidden cost comes directly from the specific Q-learning objective they use to teach the model when to halt.
Q-learning, like reinforcement learning.
Sort of, yeah. It's framed as learning a policy for halting. To calculate the total ACT loss function, you actually need 2 components. There's the halting loss, and then there's the continue loss.
Okay, let's break that down. What's the ACT halt loss?
The halt loss is pretty straightforward. It's essentially a binary cross-entropy loss. It compares the model's predicted probability of halting at the current step, let's call this color, with the target value.
And the target is a based on whether the current answer is correct?
Exactly. The target halt signal is 1 if the model's current prediction matches the true ground truth answer and dollars otherwise. So the loss is 0.5 times text binary cross entropy, PUOOP dollars. It encourages the model to predict halting when its answer is correct.
Okay, that makes sense. Learn to stop when you're right. What's the problematic part? The ACT continue loss.
Yes, the continue loss is the tricky one. To compute this loss, the model needs to estimate the value of not halting the value of continuing for one more step. It needs to know if running one more refinement step would have yielded a better result, example, a correct answer if the current one is wrong, compared to halting now.
Okay. But how does it know that? Does it have
Yep.
to look into the future?
Effectively, yes. It has to run a counterfactual. To calculate the continue loss properly, the HRM implementation requires performing an extra complete forward pass through the entire HRM architecture, FIFL, FL, FH, FOA, starting from the current state, Zivaliras.
Wait, a whole extra forward pass just to calculate part of the loss for the current step?
Exactly. The pseudocode in the HRM paper confirms this. You have to compute ziblio ziz, zilli se to see what would happen if you continued one more step.
Oh, wow. So let me get this straight. For every single optimization step during training, you do the normal forward pass to get your prediction idle or not, and halting probability $2. Then, to calculate the full ACT loss, you have to do a second full forward pass just to figure out the continue loss component.
That's precisely it. So while ACT was great at reducing the number of supervision steps, the way it was implemented meant it effectively doubled the computational cost of each individual step that was actually performed.
That's a significant hidden tax. 2 forward passes for every 1 optimization update.
It is, and this complicated, theorem-dependent via IFT and computationally extensive via ACT's continue loss structure of HRM really set the stage for TRM.
Right. The TRM approach basically looked at all this complexity and asked, what if we just get rid of it?
Exactly. What if we strip away everything that relies on that shaky fixed point theorem? What if we simplify the architecture? What if we find a cheaper way to handle adaptive computation? That's the philosophy behind the tiny recursion model.
Okay, so TRM arrives on the scene and fundamentally rejects HRM's core premise, the reliance on the implicit function theorem and the memory-saving but mathematically dubious one-step gradient approximation.
Right. The TRM insight was basically, since the mathematical basis for that IFT shortcut wasn't really holding up in practice anyway, why bother with it?
So what was the TRM solution? It sounds radical in its simplicity based on the outline.
It was. They decided to remove the approximation entirely and just perform full backpropagation through the final recursive sequence.
Full backpropagation,
Yeah.
meaning track the gradients through all the steps in the last refinement cycle.
Exactly. This is a massive shift from HRM's only track the last 2 steps approach. In TRM, there is no Diaches call happening within the final reasoning cycle that's used for learning.
Okay, so they define this concept of a full recursion process. What does that entail?
A full recursion process in TRM typically contains 1 evaluations of latent reasoning steps, followed by 1 evaluation of an answer refinement step. We'll get into the specifics of the single network soon, but think of it as a sequence of $1 plus $1 operations.
And unlike HRM, which only tracked gradients for steps 5 and 6 out of its 6-step process,
TRM tracks gradients through that entire sequence of $1 plus $1 steps during the final learning phase.
But wait, we just discussed how backpropagation through time, BPTT, for long sequences, is memory intensive. If TRM uses full BPTT over $1 plus the longest steps, and maybe $1 is reasonably large, wouldn't that just blow up the memory, cause out-of-memory OM errors?
That's the critical challenge they had to solve. And this leads to TRM's key engineering innovation, which they call the deep recursion strategy. It's how they get the benefits of deep supervision, multiple cycles of refinement, without the memory cost of full BPTT over all those cycles.
Okay, how does the deep recursion strategy work?
It's actually quite clever. Let's say you want to benefit from $2 cycles of refinement. Similar to HRM's, TRM runs the first T-Bonner of these full recursion processes completely without gradients.
Ah, so they use the Torch.Nograd context or equivalent.
Exactly. For the first T-Done cycles, they just iteratively update the latent state, which in TRM becomes the solution estimate dollars and the reasoning state purely for refinement without building up any gradient history.
Okay, so they improve the state over T-Donor cycles without paying the memory cost.
Yeah.
Then what?
Then, for the final T-Down cycle, they run that same full neckly plus $1 step recursion process again, but this time with backpropagation enabled.
I see. So the gradients are only calculated and stored for that very last cycle of refinement.
Precisely. This strategy is their workaround for the BPTT memory problem. They get the powerful generalization benefits that come from deep iterative refinement, running 2-cycles, but they only pay the memory price for tracking the gradients through one full reasoning sequence, the last one.
That's smart. You get most of the benefit with only a fraction of the memory cost
Mm.
compared to BPTT over all delta cycles.
Very smart. And the results validated this approach dramatically. The paper reports that when they tried implementing TRM but kept the old IFT detach method from HRM, the accuracy on Sudoku-Extreme was only 56.5%.
Okay.
But when they switched to this deep recursion strategy with full back propagation through the final cycle, the accuracy jumped massively to 87.4%.
Wow, it's a huge difference from 56% to over 87%.
It really is. It strongly confirms that the ability to track the gradients properly through the entire final sequence of refinement steps, letting the learning signal flow back through all $1 plus cell run operations, is absolutely key to achieving strong generalization on these structured reasoning tasks. The IFT shortcut was leaving a lot of performance on the table.
Okay, so TRM fixes the gradient problem by using full back prop on the last cycle. What about those latent features? HRM had 6 endeavors, the low-level and high-level states, justified by those perhaps questionable biological analogies. Did TRM keep those?
No, TRM simplified this dramatically as well. They ditched the ZH-Derder terminology and the complex justifications and instead focused purely on what was functionally necessary for the model to work.
And what did they conclude was functionally necessary?
Their reinterpretation is really elegant and intuitive. They found that HRM's so-called high-level feature, ZHOD, was functionally acting as just the current embedded representation of the solution.
So CRH was basically tracking the answer grid itself.
Essentially, yes. And the so-called low-level feature, CHRMs, was functionally acting as the dedicated latent reasoning feature, Z-up. This is the hidden state that carries the intermediate thought process, the scratch work.
Okay, so instead of ZOJs and CRDM, just thinks in terms of UH of the current answer, and COJ, the hidden reasoning state. That seems much clearer.
It really is. And they provided evidence for this interpretation too, apparently using visualizations in their work. They showed that the tensor structure corresponding to HRM's Zio-over-Ado clearly tokenizes or decodes into the predicted output grid, like the Sudoku numbers,
Okay.
whereas the tensor corresponding to IRADU remained an abstract, undecodable, latent feature. It was clearly holding the intermediate reasoning trace, not the solution itself.
That makes a lot of sense. Let's use an analogy the outline suggests.
Yeah.
Your dollars is like the final answer sheet you're filling in.
Yay.
And old dollars is like your separate notepad or scratch paper where you do all your intermediate calculations, try things out, keep track of constraints.
Perfect analogy. Enable holds the current best guess for the answer. ZIRV holds the working memory or reasoning process that leads to refinements of dollar.
And the TRM argument is that you absolutely need both of these. Why?
Well, think about it. If you only carried the solution feature, yai, just the answer sheet, the model would have to somehow cram both the current state of the answer and the entire reasoning trace that led to it into the limited capacity of yars. It would lose its dedicated space for complex reasoning. The answer representation would get polluted with calculation history.
Okay, so you lose reasoning capacity if you only have Yallers. What if you only had Deliber, the reasoning notepad?
If you only carried the reasoning feature Zeliber, the model would have this abstract thinking space, but it wouldn't have an explicit place to store the concrete answer it's building towards. It would constantly have to reconstruct the current solution state from the reasoning trace.
So Zeliber would waste its capacity just remembering the current answer rather than focusing on the next reasoning step.
Exactly. So the conclusion is you need both. You need Deliber to represent the explicit current answer state, and you need a separate dealer to hold the implicit latent reasoning trace that operates on and refines Dealer.
That feels very intuitive. Does the research back this up with experiments, like trying TRM with only one feature?
Yes, the ablation studies reported in the paper strongly support this two-feature design.
What did they find?
When they tried forcing TRM to use only a single combined latent feature, let's call it single ZIL, the accuracy on Sudoku-Extreme dropped significantly, down to 71.9%.
Okay, so much worse than the two-feature version. What about trying more features? Maybe the ZLDH idea wasn't wrong, just needed more scales.
They tested that too. They tried a version with multi-scale reasoning features, effectively splitting dollars into $1 plus 177 different latent tensors, perhaps trying to mimic different levels of abstraction more explicitly.
Nope. Performance was better than the single feature, but still worse than the simple two-feature model. This multi-scale version only reached 77.6% accuracy.
Wow. So one feature's too few, seven features are too many. Exactly. The optimal configuration, the one that achieved the headline 87.4% accuracy, was the simplest functional design. Just the two features, yellers for the solution and zollers for the reasoning. It shows that clarity of function and simplicity won out over forced complexity or unnecessary constraints. Hashtag 2.3, the less is more, architectural choices.
This philosophy of simplification seems to run through the entire TRM design. It's not just the gradients and the latent features, it extends to the architecture itself, right? This is where the tiny recursion model really comes from.
Absolutely. The drive was to minimize parameters wherever possible, as long as it didn't hurt, and ideally helped, generalization on these small structured data sets. This led to a series of deliberate architectural choices.
Okay, let's go through them. First, the single tiny network. You mentioned HRM used two distinct four-layer transformer networks, $5 and $5. That seems redundant if they're doing similar processing.
It was redundant. TRM recognized this. HRM had separate networks, effectively doubling the parameter count for the core reasoning logic. TRM realized a profound, simple truth. The task being performed, whether it's updating the reasoning state or refining the solution, is implicitly defined purely by the input signature given to the network.
What do you mean by input signature?
Well, think about the two main update steps in TRM. The latent reasoning update needs the original question context, $6, so its call looks like left arrow net, XYZ. It needs the problem definition.
Okay.
But the solution refinement step, which updates based on the latest reasonings, arguably doesn't need the original question's $6 again. Its call looks like left arrow net or Z, it just needs the current solution in the reasoning trace.
Ah, I see. So the network can tell which job it's supposed to do just by checking if the input $6 is present in its input arguments.
Exactly. A single network module can perfectly learn to perform both goals. It implicitly adapts its function based on whether $6 provided.
That's ingenious. You don't need two separate sets of weights.
Nope. This simplification instantly halved the number of parameters in the core reasoning block compared to HRM. And crucially, it didn't just save parameters, it actually improved generalization. The paper showed accuracy went up from 82.4% with two networks to 87.4% with a single shared network.
Less is more, literally. Fewer parameters led to better results.
Oh.
Architectural economy paying dividends.
Precisely. Okay, second architectural choice, optimal depth.
Right. For typical LLMs, the scaling mantra is deeper is better. Add more layers. TRM found the opposite.
The exact opposite, yes. When they experimented with increasing the number of layers within the single TRM network module, the net function, going from maybe 2 layers up to 4 layers like HRM used,
Performance got worse.
performance got significantly worse. Generalization decreased because the larger network started to severely overfit the relatively small structured data sets they were training on.
So what was the optimal number of layers within the network?
The optimal finding was just 2 layers. A 2-layer network maximized generalization.
Only 2 layers. That seems incredibly shallow.
It is incredibly shallow in terms of feed-forward depth, but this highlights that crucial distinction we touched on earlier. TRM achieves its effective depth through deep recursion over time, not through deep feed-forward layers stacked in space.
Right. Can we recalculate the effective depth for the final TRM model using the optimal parameters? The outline says TT at 3 cycles, 1n6 latent steps per cycle, and now we know min layers 2, 2.
Okay, so the effective depth is T2 times n plus 1 times n text layers. That's $3 times 6 plus 1 times 2.
$3 times 7 times 2 equals 42, 2.
42 layers of effective computational depth achieved by repeatedly applying a simple 2-layer network over time. That's how it gets its expressive power, not by being a deep network itself.
Fascinating trade-off. Okay, third simplification. Attention-free architecture. This sounds radical too. Transformers are built on self-attention.
They are. But TRM found that for certain tasks, specifically those with a small fixed context length, the standard transformer self-attention mechanism wasn't actually necessary and might even be overkill.
Like the 9x9 Sudoku grid, 1 and 8111. That's relatively small compared to text sequences.
Exactly. When the sequence length lollers is small and fixed, the global context mixing provided by self-attention might provide less benefit compared to its quadratic computational cost.
So what did they replace it with?
They found that replacing the self-attention layer with a much simpler channel mixing MLP layer, inspired by architectures like MLP Mixer, actually worked better for these small context tasks.
Just an MLP processing across the channels or features instead of attending across position.
Essentially, yes. And this attention-free structure significantly improved generalization on Sudoku-Extreme, taking accuracy from 74.7% with attention up to the final 87.4% with the MLP layer.
Another win for simplification. But there's a caveat here, right? This doesn't work everywhere.
Correct. Very important caveat. For tasks involving larger context lengths, like the 30 by 30 grids used in the Mazehard benchmark or the variable size grids in ARCAGI.
The MLP replacement wasn't good.
No, it was suboptimal there. On those larger grids, the inductive biases and the global context aggregation capability of standard self-attention were still necessary or at least beneficial. The attention-based TRM performed better on Mazehard and RCAGI.
So the architectural choice between attention and MLP depends on the task's context size. Makes sense.
Yeah. Okay, fourth, simplification. Simplified ACT. We heavily criticize HRM's adaptive computational time implementation because of that hidden cost the second forward pass needed for the Q-learning continue loss.
Right. Did TRM fix that?
They did. They simply removed the continue loss entirely.
Just got rid of it. So the ACT loss in TRM is only based on the halting probability.
Exactly. The loss formulation simplifies dramatically. It just becomes the binary cross-entropy between the predicted halting probability and whether the current answer is correct, plus text binary cross-entropy. That's it. No counterfactual needed.
And this eliminated that expensive second forward pass.
Completely. It made training effectively twice as fast per optimization step compared to HRM's ACT because now each step only requires one forward pass.
But did removing the continue loss hurt performance? Did the model forget how to decide when to continue?
Apparently not. Crucially, this simplification resulted in no significant drop in accuracy. The final accuracy remained high, around 87.4%, List says, 86.1% in one comparison. This strongly suggests that the complex counterfactual calculation in HRM's ACT was unnecessary baggage. The simple halting loss was sufficient to learn an effective stopping policy.
Wow. Simpler, faster, and just as good. That's a clean win.
Definitely. And finally, the fifth point, exponential moving average, EMA. This isn't strictly architecture, but a training technique.
EMA of model weights. Why was that needed?
Given the very small data sets, remember 1,000 examples per task, training could be quite unstable. The model weights could shift too aggressively from one batch to the next, leading to sudden drops in performance, what they call sharp collapse or even divergence.
Okay, instability due to small data.
Right. So they integrated exponential moving average, EMA, of the model weights during training. This means the weights used for evaluation and potentially for the next training step's forward pass are not just the latest weights, but a smooth, weighted average of the weights over recent history. They used a high decay rate, like 0.999.
And this helps stabilize things.
Yes, it smooths out the sharp updates, prevents the model from jumping into bad regions of the loss landscape, helps it settle into broader, more robust minima, and generally prevents overfitting.
Did it make a big difference to generalization?
It did. They reported that adding EMA reliably boosted generalization accuracy from around 79.9% up to the final 87.4% on Sudoku-Extreme. It was a crucial component for getting stable, high performance on these small data sets.
Okay, so TRM's success comes from a whole suite of simplifications. Single shared network, shallow feed-forward depth compensated by deep recursion, context-dependent attention MLP choice, simplified ACT, full backprop on the last cycle, and EA for stability. It's a holistic approach.
Exactly. Less is more, applied consistently across the board.
Okay, we've dissected the architectures and the reasoning behind TRM's design. Now let's look squarely at the results. We have to keep reminding ourselves of the parameter gap here.
It's staggering, isn't it? TRM is operating in the, 5 million to maybe 19 million parameter range, depending on the variant.
While HRM was around 27 million. And the LLMs we're comparing against are in the hundreds of billions or even trillions of parameters. DeepSeek R1 at 67B, Grok, it's orders and orders of magnitude difference.
An absurd gap. Yet the performance reversal on these specific reasoning tasks is even more stunning when you look at the tables in the paper.
Let's start with that core structured logic benchmark. Sudoku-Extreme. Small data, but requires hard, consistent reasoning.
Right. Here, the TRM variant using the MLP layer, since context is small, the TRM MLP model achieved 87.4% accuracy.
87.4%. How did HRM do?
HRM only managed 55.0%. A huge gap already.
And the LLMs. The big ones trained with chain of thoughts prompting.
The paper reports they essentially scored 0.0%. They just couldn't reliably solve these extreme difficulty Sudoku puzzles generated using their specific procedure.
0%. That just perfectly illustrates the point, doesn't it?
Huh.
For this kind of structured logic, the architectural approach of TRM, this recursive refinement, absolutely crushed the brute force scaling approach of LLMs. Structural intelligence beats scale here.
Completely. It's not about knowing facts. It's about applying consistent logical rules iteratively.
Okay, what about tasks with larger context? Does TRM still hold up? Let's look at Maze Hard. These are 30 by 30 grids, right? So $11,900?
Yes, much larger context. Here, the attention-based TRMM variant, TRM-AT, was needed, as we discussed, and it scored 85.3% accuracy.
85.3%.
Yeah.
Still very high. How did HRM compare on Maze Hard?
HRM scored 74.5%, so TRM still significantly outperformed HRM even on this larger scale task. The simplification benefits carried over.
Okay, impressive consistency. Now, the ultimate challenge, ARC-AGI-2. This is that frontier AI benchmark for abstract visual reasoning.
Yeah.
Extremely difficult.
The toughest one they reported on. And here, TRM-AT, remember, this is likely the tiny 7 million parameter version achieved 7.8% accuracy.
7.8%. Now, that sounds low in absolute terms, but how does it compare?
It's low, yes, because the task is incredibly hard for current AI, but compare it, HRM only got 5.0%.
Okay, so TRM is better than its predecessor. What about the big guns? Gemini 2.5 Pro?
Gemini 2.5 Pro, using presumably massive compute and test time techniques, was reported at 4.9% on this benchmark in the source materials context.
Wait, so the 7 million parameter TRM actually outperformed Gemini 2.5 Pro on ARC-AGI-2?
According to these results, yes. 7.8% for TRM-AT versus 4.9% for Gemini 2.5 Pro. It demonstrates superior efficiency and generalization capacity, even in this incredibly difficult domain that requires abstract, almost analogical reasoning. It's finding better solutions with vastly less compute and parameters.
That is genuinely remarkable. A tiny model beating a state-of-the-art giant on a task designed to push AI reasoning limits.
It really highlights the potential of this recursive approach for certain problem classes.
Let's circle back quickly to those optimal recursion parameters you mentioned, because this touches on the trade-off TRM made by using full backpropagation.
Right. They found the sweet spot for TRM was typically around T3-hour cycles of refinement and 1 M63 latent reasoning steps within each cycle.
Okay, T2 to $3 and $67.
Yep.
Which gives us that effective depth of TRs teen plus 1 times n layers, 3 times 7 times 2 of 42 layers we calculated. How did that compare to HRM's typical settings?
HRM used lower settings, usually TT2 cycles and ANQUIL 2 steps within the cycle. Although the forward pass had $3 and preorbital calls, the core loop parameters were TT2 and 2.2. This gave it less effective recursive depth per pass, maybe around 20 layers per pass times 1 of steps. The total depth could be high, but the depth per learning step was shallower. TRM favored deeper recursion within the final backpropagated cycle.
And did they find limits to pushing nuller the number of steps within a TRM cycle?
Yes. As we predicted, the paper notes that pushing nuller too high acuity beyond 6 or 7 did predictably lead to out-of-memory errors during training.
Because the computational graph for the backpropagation just hit so big.
Exactly. That's the direct price you pay for doing full BPTT through that final N plus $1 sequence. The memory scales with numblers.
So there's a hardware limit.
There is. However, the authors explicitly state that the generalization boost they got from increasing num$ up to that limit, around 1 into 66, was substantial. They basically said the performance gain was well worth its price in gold.
Meaning they consciously accepted higher training memory consumption, requiring a better GPUs perhaps, in exchange for getting massive improvements in the final model's accuracy and generalization.
Exactly. It was a deliberate trade-off. Use more memory during training to enable full gradient flow through a deeper final recursion, because that's what delivered the state-of-the-art results. Hashtag tag 3.2, the critical role of data augmentation.
Okay, these results are incredibly strong, especially given the model sizes. But we need to pause here and add some crucial context, right? This amazing performance isn't just about the tiny model's architecture being magical on its own.
No, absolutely not. That's a critical point. The TRM architecture is incredibly efficient at learning from data, especially small data, without overfitting. But its success relies heavily, fundamentally, on having access to high-quality, task-specific data augmentation.
Because the base number of training examples is tiny, like 1,000.
Yeah, often just around 1,000 human-labeled examples per task. That's nowhere near enough to train even a 7 million parameter model robustly without massive overfitting, unless you can artificially expand the data set.
So data augmentation is the fuel, and TRM is the efficient engine.
That's a great way to put it. TRM's architectural strengths, simplicity, recursion, EMA, prevent it from just memorizing the small training set. But the augmented data is what provides the variety and coverage needed for it to learn the underlying rules and actually generalize to new, unseen problems. The quality and quantity of the augmentations are non-negotiable here.
Can we look at the specific types of augmentation used for each task? They seem tailored.
They are. For Sudoku-Extreme, they used shuffling augmentations.
Shuffling. How does that work for Sudoku?
You take a solved Sudoku grid. Then you can apply permutations that preserve the Sudoku rules. For example, you can swap rows 1 and 2 if they are within the same 3x3 block band. You can swap columns 4 and 6, again within the same vertical band. You can also permute the numbers themselves, like changing all 1s to 8s, all 8s to 3s, and all 3s to 1s consistently across the grid.
Ah, so these shuffles create new grids that look different but are structurally identical in terms of the underlying logic.
Exactly. They generated 1,000 such shuffle augmentations for every single original Sudoku sample. This massively expands the effective dataset size, teaching the model the abstract rules rather than specific number placements.
1,000 augmentations per sample. Okay, that's significant. What about maze hard? That's visual.
For the maze grids, they relied on spatial transformations,
Yeah.
specifically the 8 dihedral transformations.
Dihedral, meaning rotations and flips.
Yes, you take the maze grid and you can rotate it 0, 90, 180, 270 degrees, and you can also flip it horizontally and then apply the rotations. That gives you 8 unique orientations of the same maze.
And the idea is the correct path through the maze should be the same, logically, regardless of how the grid is oriented.
Precisely. It teaches the model rotational and reflectional invariance, which is important for spatial reasoning.
Okay. And for the really complex ARC-AGI benchmark, that involves colors and shapes and transformations.
Yeah, ARC requires more sophisticated augmentation. They used up to 1,000 augmentations per puzzle there, too, combining several techniques.
Like what?
Color permutations, changing the colors used in the input-output grids consistently, dihedral group transformations again for spatial invariance, and also translations, shifting the patterns within the grid.
And the goal here is to force the model to learn the abstract concept of the puzzle's transformation rule, rather than just memorizing the specific pixel patterns or colors of the single example pair it sees.
Exactly. If the rule is fill the largest shape red, the model should learn that rule whether the shape is blue or green initially, whether it's in the top left or bottom right, whether the grid is flipped. The augmentations force that abstraction.
So it's this powerful synergy then. TRM's lean architecture prevents overfitting on the small base data, while the massive, high-quality augmentation provides the rich signal needed to learn the generalizable underlying structure of the problem.
That's the winning combination here. You need both. The tiny model on its own wouldn't generalize without the augmented data, and a huge model would likely just overfit even the augmented data without the right inductive biases like recursion. Hashtag tag 3.3 failed ideas and final synthesis.
Before we wrap up this deep dive, it's often illuminating to look at the experiments that didn't work. The paper mentions a few ideas that failed. What can we learn from those?
Yeah, negative results are often just as informative. First, they tried swapping out the simple MLP layers used in the attention-free variant for a mixture of experts, MOE layers.
MOEs are usually used to increase capacity efficiently in large models. Did that help here?
No, it hurt. Generalization decreased significantly. The interpretation is that MOEs added far too much capacity for these small, structured data sets, leading to even worse overfitting than a standard dense network of equivalent size might have. Too much flexibility was detrimental.
Interesting. So keeping it simple was key. What else failed?
Second, they tried to find a middle ground on the backpropagation. Remember, HRM tracked only the last 2 steps, and TRM tracked all $1 plus $1 steps in the final cycle. They experimented with tracking just TLR steps, where $2 ham plus $1.
A compromise.
Yeah.
Trying to save some memory compared to full TRM, but get more gradient signal than HRM.
Exactly. But apparently this compromise did not help generalization either. It seems you really need the full gradient flow through the entire final recursion sequence. 2 Kilium plus $1. To get the best credit assignment and performance, half measures didn't work.
Okay, full backprop or bust, basically.
Yeah.
Any other failed ideas?
Third, they went back to that fixed point idea. They tried using a specialized library, TorchDQ, which is designed to rigorously find the fixed point of a recurrent function using numerical methods, and then use the IFT for gradients. This would have, in theory, put HRM's original premise on a much firmer mathematical footing.
Okay, so did using a proper fixed point solver help?
Surprisingly, no. It significantly slowed down the training process, as finding the fixed point numerically takes time. And even worse, it actually led to poorer generalization compared to TRM's simple iterative refinement with backprop.
Wow. That's perhaps the most damning finding against the whole fixed point justification, isn't it?
It really is. It strongly suggests that converging precisely to a mathematical fixed point is not essential and maybe not even desirable for solving these kinds of problems effectively.
So what is essential then, if not convergence?
It seems the key is the iterative refinement process itself. The ability to repeatedly apply the reasoning network over multiple steps and cycles, allowing the solution and reasoning state to gradually improve, combined with the ability to get a clean learning signal via backpropagation through that entire refinement sequence, at least the last cycle. Convergence is secondary to the process.
Okay, one more failure.
Just a small architectural one. They tried weight tying between the input embedding layer and the output head. This is sometimes done in language models.
Did it work?
No, it hurt performance. It was apparently too strong a constraint for these models. They needed the flexibility of separate input and output mappings.
Okay, so let's try to synthesize this. If we connect all these pieces to the bigger picture, what's the core takeaway from the HRM to TRM evolution?
I think the core takeaway is the triumph of, well, radical simplification guided by empirical results and functional necessity, combined with the power of deep temporal processing through recursion.
So TRM identified the most valuable component of HRM, which was that idea of deep supervision iterating over time.
Yes, but it jettisoned the baggage. The complex architecture with two networks, the shaky IFT justification, the expensive ACT, it replaced them with a single tiny network, a robust full back propagation strategy for the final cycle, managed via the deep recursion strategy, and a simplified ACT.
And it reconceptualized the latent state not through biological analogies, but through functional roles. Yellers for the solutions, Eulers for the reasoning.
Exactly. By pairing the simplified, trackable, recursive core, Euler single network full backprop, with deep supervision, multiple cycles, TLRs, TRM manages to effectively simulate massive computational depth, those 42 layers calculated using a physically tiny model.
Which allows it to remain parameter efficient, minimize overfitting on small data sets, especially with EMA and augmentation, and ultimately dominate these highly structured logic-based reasoning tasks where giant LMs fail.
That's the story, I believe. Architectural simplicity plus intelligent recursion over time.
So what does this all mean for the field? It strongly suggests that for certain classes of problems, particularly structured hard reasoning tasks, this path of architectural simplification combined with smart recursion might be far more effective and vastly more efficient than the prevailing wisdom of just scaling up autoregressive LLMs indefinitely.
It certainly challenges the scale is all you need narrative for these domains. Hashtag tag outro.
Well, we really dove deep there. We successfully unpacked the rather complicated, assumption-laden structure of the original hierarchical reasoning model, HRM, with its two networks, its reliance on the implicit function theorem, its costly ACT mechanism.
Yeah, and then we saw how the tiny recursion model, TRM, came along and just simplified almost everything. One tiny two-layer network doing double duty, full back propagation, but only through the final recursion cycle to save memory. A much leaner approach to adaptive computation time.
And this radical simplification wasn't just for elegance. It was driven by performance. It allowed TRM, with maybe just 7 million parameters, to achieve truly superior results on notoriously hard puzzles like Sudoku-Extreme and even the ARC AGI benchmark.
Results that significantly beat not only its predecessor HRM, but also state-of-the-art large language models that are hundreds of thousands, if not millions of times larger in parameter count. It really confirms that sometimes the constraint of size forces you to find a more intelligent, more structurally sound solution.
And that structural solution, achieving 42 layers of effective depth via recursion in time, rather than stacking layers in space, is just undeniably elegant.
It is, but as the authors themselves honestly note, despite these incredible empirical gains, the fundamental question of why exactly this deep recursion helps so much, compared to just trying to build an equivalently deep feed-forward network, that remains largely unexplained theoretically.
They suspect it's related to overfitting. that the shared weights across time act as a strong regularizer.
That's their main hypothesis, yeah. That the recursive structure inherently resists overfitting on small data much better than a deep feed-forward net with unique weights at each layer would. But they admit there's no current mathematical theory or framework to really formalize this advantage rigorously. It works, but the deep why is still a bit fuzzy.
Which opens up interesting future questions. If recursion is this new, powerful path to achieving effective depth, especially for supervised reasoning tasks, how do we develop scaling laws for it?
Exactly. We have scaling laws relating performance to parameter count, data size, compute, but we don't really have established laws for how performance scales with recursive depth in these kinds of models. How do you optimally parameterize them? That's a whole new area to explore.
And maybe a more practical question looking ahead. HRM and TRM, as presented, are supervised methods, right? They learn to map a specific input problem to a single deterministic correct output.
Correct. They excel at tasks with one right answer, like Sudoku or finding the single path in a maze.
But many real-world problems are more open-ended, more generative. There might be multiple valid solutions, or you might want to generate creative text or code. Can these powerful, efficient, recursive structures be extended beyond supervised tasks? Can they be adapted to handle generative modeling?
That's a huge open question. Could you combine the iterative refinement strength of TRM with the generative capabilities of, say, diffusion models or other frameworks? Could you build a generative TRM? That's definitely something for you, the listener, to mull over, or perhaps something researchers are already starting to explore. A fascinating direction for future work.
Welcome back to the Deep Dive. Today, we are tearing into a piece of research that, well, it really challenges the whole AI development paradigm we've seen for the last, decade.
Absolutely. It's that core belief that the only way to get towards general intelligence is just massive, massive scale.
Right. Bigger is better. More data, more compute, billions, hundreds of billions of parameters.
Yeah, for years, if a model wasn't quite cutting it, the default answer was just scale it up, make it bigger.
The paper we're diving into today flips that on its head.
Mm.
It argues that for certain kinds of problems, specifically complex step-by-step reasoning, a really carefully designed tiny network can actually outperform the giants.
And not just compete, but actively beat them. That's the kicker.
And when we say tiny, we mean minuscule, right?
We do. We're talking about these tiny recursive models, TRMs. Some versions have as few as like 7 million parameters.
7 million. Okay, put that in context.
Well, the headline finding, the really shocking claim, is that these 7M parameter TRMs get higher accuracy on really tough puzzle tasks. Think specific subsets of the ARC-AGI benchmark than models like Gemini 2.5 Pro or DeepSeek R1.
Which have how many parameters? Hundreds of billions.
Exactly. So 7 million is less than 1/10,000th. I mean, it's less than 0.01% of the parameter count of these state-of-the-art large language models. It's staggering.
Wow. So it's not about the raw size then.
Apparently not for this type of reasoning. The TRM architecture seems to prove that structured, deeply recursive computation, when it's implemented with real mathematical rigor, is just much more effective for symbolic reasoning than, throwing brute force compute at it.
Okay, let's really dig into this. We need to unpack it with the rigor it deserves, right? Our mission today is to understand the architecture, the math, the notation, the logic behind how TRM works.
Mm-hmm.
And crucially, compare it to what came before it, this hierarchical reasoning model, or HRM. We need to see how this simplification, this move to tiny, actually leads to better generalization.
Right. And to do that, we probably need to start with why the big models, the LLMs, struggle in the first place. What's their fundamental weakness on these kinds of tasks?
Yeah, let's start there. Section 1. When you look at these hard question-answer problems, the ones needing focused multi-step logic, like, say, really difficult Sudoku variants or abstract visual puzzles, the LLMs just seem to hit a wall, don't they? Even the best ones. The paper calls it the brittle answer problem.
It really boils down to their core design philosophy, autoregression. An LLM generates its output token by token, one after the other. Sequentially. So imagine it's trying to solve a complex math proof or follow a long chain of logical steps. If it makes just one mistake, one single incorrect token, say in step 5 of a 20-step process,
That mistake gets baked in.
it gets baked in.
Yeah.
That wrong token becomes part of the input for generating the next token and the next and so on. There's no inherent mechanism for the model to just pause, step back, rethink that one specific step, and correct itself locally.
So One slip and the whole thing can unravel. The entire complex solution gets invalidated by that single point of failure.
Precisely. It's brittle.
Okay, but developers know this, right? They have workarounds. The paper mentions chain of thoughts, code T, and test time compute, TTC. What are those trying to fix?
They're trying to mitigate that brittleness, essentially. Chain of thoughts, which really took off around 2022, tries to make the model behave more like a human reasoning.
How so?
It prompts the model to generate an explicit sequence of intermediate steps like a thinking process before it gives the final answer. The idea is that this reasoning trace guides the model towards a more logical conclusion.
And does it work?
It definitely helps. It boosts performance on many tasks. But, and this is a big but, it has drawbacks. First, you need massive amounts of high-quality data showing step-by-step reasoning to train it effectively, which is expensive to create. And second, it's still fundamentally brittle. If the chain of thought itself contains a logical flaw, the model will likely follow that flawed reasoning to a wrong answer, often with high confidence. It just gives you a more plausible-sounding, incorrect answer.
So it's like a slightly less brittle way to be wrong.
You could put it that way, yeah.
Okay, what about TTC? Test time compute. That sounds more like a statistical fix.
It is, exactly. TTC is basically trying to average out the randomness or find the most common path. You make the LLM generate the same answer multiple times, say $T2 times maybe 10, 20, even more different attempts at the solution.
And then you just pick the most popular one.
Pretty much. You either report the answer that appears most frequently in those samples, hoping the majority is correct, or sometimes you use a reward model to score each attempt and pick the highest scoring one. It's using statistics to try and suppress the outliers, the random mistakes.
But even with these fixes, CART and TTC, the performance on these specialized hard reasoning tasks, it's still not great, is it? The source mentions the ARC-AGI-2 benchmark specifically.
Yeah, the IRC-AGI benchmarks are really designed to probe abstract, fluid reasoning, not just pattern matching or knowledge recall. And on ARC-AGI-2, which is a newer, tougher subset, even the really sophisticated models like Gemini 2.5 Pro, reportedly using these expensive TTC methods, only managed about 4.9% test accuracy.
4.9%.
Well, it's low, incredibly low. And that single data point really hammers home the message. For true complex algorithmic reasoning, that just scale it up paradigm seems fundamentally broken. There's a massive gap.
And that performance gap, that frustration presumably led researchers to explore completely different architectures.
Exactly. It motivated the development of models specifically designed for deep iterative reasoning, which brings us to the direct predecessor of the model we're focusing on today, the hierarchical reasoning model, or HRM.
Okay, let's dive into HRM then. Section 1.2. This is the first real breakthrough, wasn't it? Showing that supervised models, if built the right way for recursion, could actually get high accuracy on tough stuff like Sudoku-Extreme, maze pathfinding, and the original ARC-AGI tasks.
That's right. HRM made waves because it worked surprisingly well on these problems where LLMs struggled. And its success really came down to two main architectural ideas, two novelties.
What were they?
The first was recursive hierarchical reasoning, and the second was deep supervision. Now, unlike LLMs, which generate text, HRM is a supervised model. You give it an input, like a puzzle, and it produces a deterministic output, the solution. The magic was how it used small network components recursively to create something effectively very deep and powerful.
Okay, let's break down that first part.
Yeah.
Recursive hierarchical reasoning. How did that work architecturally? It sounds like there are levels involved.
There were. HRM used two distinct small neural networks. They were typically 4-layer transformers. The authors labeled them $5, and
$5, okay.
$5 was meant for low-frequency updates and $5 for high-frequency updates. These two networks operated on two corresponding latent feature vectors, two internal states. So ZAL is for low-level stuff and ZAR for high-level. That was the intuition. ZH-RLs was conceptualized as representing the detailed step-by-step reasoning, kind of like a mental scratch pad. ZH-LRs was thought to hold the more stable, high-level state, maybe the current working solution or an abstract representation of it.
And they didn't just update in parallel. There was a structure, a hierarchy.
Precisely. There was a defined interaction. The original HRM paper actually motivated this with a biological analogy, talking about different temporal frequencies and brain processing.
Oh, interesting. So like fast and slow thinking.
Kind of. The idea was, say our own handles the rapid, frequent updates, the sort of low-level computational grind, while ZH-RL gets updated less often, integrating the information from ZH-RL to maintain the overall solution structure.
Okay. And how do they interact mathematically?
The crucial part is the update rule. Both latent features, z-edgeral and z-edgeras, were actually fed as inputs into both networks and fireworks during the iterative update cycle, along with the original problem input. It was this complex interplay justified by this biological analogy, which, as we'll see, the TRM paper later argues is maybe unnecessary complexity.
Right, simplifies things later. But first, the second pillar of HRM, deep supervision. This sounds like how they get that effective depth without just making the networks huge.
Exactly. Deep supervision is the trick to making shallow networks act deep. Instead of one single learning step, HRM breaks the process into multiple, smaller supervision steps. Let's call the maximum number of these steps nonetexus. In the paper, they typically use nonetexup 16 steps.
In each of these 16 potential steps, the model tries to refine its output prediction. Let's call it adioshi. And here's the critical part. After each step, the latent features from that step, 16 or earlier, are carried over and used as the starting point, the initialization, for the next supervision step.
So the state persists across these steps. But wait, if you just keep chaining computations like that, doesn't the computational graph get enormous? Backpropagating through 16 steps, each involving internal recurrence. That sounds like a memory nightmare. It would be. That's where the detachment comes in. This is the absolute key to making deep supervision work efficiently. When those latent features, 7 lollers and 7, are reused as initialization for the next step,
Yes.
they are detached from the computational graph.
Detached, meaning the gradients don't flow back through them.
Exactly. This explicitly avoids standard backpropagation through time, BPTT, which would require storing the entire history of activations for all 16 steps and all the internal recursions. If you try to do BPTT on something with the effective depth HRM achieved, you'd run out of GPU memory almost instantly.
So by detaching, the gradients only propagate back through the computations within the current supervision step.
Correct. It's a clever trick. The network learns as if it unfolded over potentially hundreds of effective layers, but the memory cost for backpropagation at any given moment is only associated with the operations inside that single current supervision step.
It's really neat engineering. It's like creating temporal residual connections. You get the benefit of information flowing across these long time horizons, mimicking a very deep network, but without the prohibitive memory cost of actually building or unrolling one.
That's a great way to put it. It swaps the memory problem of BPTT for a much more manageable per-step memory requirement during training.
Okay, let's get super rigorous now. Section 1.3. We need to formalize HRM structure and really nail down this effective depth calculation. The numbers are important here. First, the input. How does it get processed?
Right. So you start with the raw input data. Let's call it tilde-x. This could be the image of a Sudoku grid or the representation of an ARC puzzle.
Okay.
This tilde-x first goes through a dedicated input network, $5, which has its own parameters, tilde-x. This network embeds the raw input into a suitable format for the main recursive part. So we get 6x at about tilde-x, and what does the echo look like? Typically, it's a sequence of embeddings. Its shape would be something like $, L, D. $, the batch size, obviously. Dollars is the context length or sequence length for a 9x9 Sudoku. 1 would be $81. And delos is the embedding dimension, the size of the feature vector for each position in the sequence. This embedded $6 is the input that feeds into the recursive core with $5 and $5.
Got it. So $6 is ready. Now the forward pass sequence itself. HRM used those two 4-layer transformer networks. Let's walk through the sequence step by step using the typical hyperparameters they reported. 1L2, meaning $2 steps per cycle, and 2 2-tellers, meaning 2 full cycles of recursion happen before the gradient tracking part kicks in. The source paper lays out 6 specific function evaluations for this setup. Let's go through them slow.
Okay, sounds good. This sequence defines exactly how the latent states sigzilars and zilars evolve during one pass before the model makes its prediction. Hedimer, remember, 1 $2 and 2 $2, so lighter $2. Cycle 1, we're T1. This is about settling the latent state. Step 1, Z option left arrow FL. CL plus CH plus X. This is the first update to ZH, the low-level reasoning feature. It takes the current CH, adds the current high-level state CHX, adds the embedded input, the CDIs, and feeds it all into the file network. Importantly, this step is done without gradients. No learning happens here, it's just calculation.
Just evolving the state.
Okay, step 2. ZL plus ZH plus X. This is the second flaw step because 1 ends else 2 FL. We update ZAC again using the new ZL from step 1, still without gradients. This completes the rapid updates for the first cycle.
Two left steps.
Step 3, ZL left arrow FH, ZL plus ZH. Now we update the high-level feature, ZH. This uses the 5 etchel network. Notice it takes the latest ZIA from step 2 and the existing ZL as input, but not the external input $6 directly in this formulation. This is the low-frequency update. And again, still without gradients. This completes the first full recursion cycle, T1.
Cycle 1 complete. State updated, no gradients tracked yet. What happens in cycle 2?
Cycle 2, we're T2, comparing the state further. Step 4, $0 left arrow FL, ZL plus ZH plus XS. We start the second cycle immediately with another file update. Now, technically, if this is part of a deep supervision sequence, the zerolas illetal used here might be the ones detached from the end of the previous supervision steps graph. But within this forward pass sequence itself, it's just another update, still without gradients.
Okay, one more 5L update. That's 4 steps total now, all without gradients. What are steps 5 and 6? This must be where the learning happens.
The final steps, tracking gradients, the learning phase. Step 5, 0 left arrow FL, ZL plus ZH plus X's. This is the final $5 update in this sequence, completing the NE2D2 steps for the second cycle. Crucially, this step IS executed with gradients. The system starts tracking the computation graph from here. This is the beginning of the sequence that the loss will backpropagate through.
Okay, so the gradient tape starts recording now.
Step 6, Z arrow, left arrow, FH, ZL plus CHO. And the final step is the 50-year update for the second cycle. This uses the Sierra 1 from step 5 and the ZO from step 3, or technically step 4 if we consider state persistence. This is also executed with gradients. This is the very last function evaluation before the final output layer.
And then after step 6?
After step 6, the final ZR state is usually passed through an output network, $5, to produce the actual prediction. For example, left arrow text argmax, CA8.doc. The loss is calculated based on ADDIE, and the gradients flow back through step 6 and step 5 only.
Okay, that clarifies it. So essentially, the model does 4 steps of warm-up or state evolution without tracking gradients, letting the internal states settle somewhat. And then only the very last 2 steps, one $5 and one Fowler, are actually part of the back propagation path.
Exactly. The first 4 steps contribute to the final state, but don't contribute to the gradient calculation memory cost. All the memory cost for backprop comes just from those last 2 function evaluations. This is how HRM claims to get deep computation cheaply.
Which brings us back to that effective depth calculation. This is the headline number, right? Taking these shallow 4-layer networks and claiming they act like a 384-layer deep network. Let's formalize how they get 384.
Right. The formula they provide for effective depth is text effective depth, text n plus 1t in text.
Okay, let's define each term rigorously again.
Text layers is the number of layers inside the 5-Weller and Fight networks. In their standard setup, that was 4 for the 4-layer transformer.
Got it. 4 layers.
Then the number of times for fibers is evaluated within one recursion cycle. In our example on 2-2.
Okay.
The 1 plus 1 factor represents the total number of network evaluations per cycle. 1 calls to $5 plus 1 call to $5, so $2 plus 1 tweeter, 3.
3 evaluations per cycle. Makes sense.
$2 is the number of these recursion cycles that run before the gradient tracking starts. In our example, $2 a dollars. These are the gradient-free warm-up cycles. Technically, the formula is a bit ambiguous here. It might mean total cycles, including the gradient one, but let's stick to the paper's likely intent matching the steps. Let's assume T represents the cycles involved in the approximation part, perhaps including the final one. The paper's explanation is a bit condensed. Let's reevaluate the example calculation they likely used. I see. The formula might be interpreted differently. Let's look at the full sequence again. 1 steps of $5, 1 step of $5 asks, that's $1 plus dollar evaluations per deep supervision step, potentially. If $2 represents repetitions within a supervision step, and 9 is the number of supervision steps. Let's reread their section 2.2 carefully. Okay, the calculation seems to assume the entire sequence within one supervision step contributes to depth. Let's recalculate based on the text.
Right, let's be precise.
Okay, the text says the total number of layers corresponds to none layers n plus 1, TNSN. Let's use their standard values. None layers 4 and $2, TTQ $2, none layers $16, plugging those in. $4 times 2 plus 1 times 2 times $16.
So $4, 3 times 2 times 16 days.
Which is $12 times 2 times $16 24 times $16. And $24 times 16 cells is indeed 384.
Okay, so the formula stands 384 effective layers. It multiplies the layers per network, 4, the steps per cycle, n plus 1, 3, the number of cycles, T2, and the number of deep supervision steps, n sub 16. That's how they get this massive effective depth from relatively small components. It's all about the temporal unfolding and the deep supervision stacking.
Precisely. It's trading parameter depth for temporal recursive depth, glued together by deep supervision. That's the core claim of HRM's efficiency and power.
It's a powerful claim, that 384-layer depth. But as you hinted, it hinges on a pretty significant mathematical shortcut. Let's move into section 2.1 and really scrutinize the implicit function theorem, IFT, and this one-step gradient approximation that HRM relies on. This seems to be where the cracks start to appear.
This is exactly where the TRM paper launches its main critique. The IFT is the mathematical tool that allows, under certain conditions, calculating the gradient of a converged recurrent process by only looking at the final step, essentially. It's the theoretical justification HRM uses for only backpropagating through those last two steps, step 5 and 6 in our example, instead of the entire sequence leading up to them.
Okay, but you said under certain conditions. What are those conditions?
The absolute key condition is that the recurrent function must have actually converged to a fixed point and equilibrium state before you apply the gradient approximation.
A fixed point, meaning if you feed the state back into the function, it doesn't change anymore.
Essentially, yes. Let's call the hypothetical fixed points for the two latent states ZL and ZIDO. Convergence means that these states satisfy the equations. A die approx FL, ZL of ZL plus CH plus X. If the state ZL has reached this equilibrium, ZH, then applying phi and Joller again won't significantly change ZLD all and ZNOs. The system has settled.
And if it has settled, then the IFT lets you calculate the gradient just based on that final settled state.
Exactly. Models that explicitly use this, like deep equilibrium models, DEQs, go to great lengths to ensure this condition is met. They often run the recurrence for hundreds of iterations using root-finding algorithms specifically to find that fixed point $0 before they even think about applying the IFT shortcut for the gradient. They prioritize mathematical rigor.
Okay, but HRM doesn't do that. It doesn't iterate until convergence.
No, it doesn't. It performs a fixed, small number of iterations in our example, just those 4 warm-up steps, steps 1, 4, and then it basically assumes that this is good enough. It assumes the state is close enough to the fixed point that the one-step gradient approximation based on steps 5 and 6 will be sufficiently accurate.
That sounds mathematically questionable. It's prioritizing a fixed computational budget, TD2C true, over actually meeting the conditions required by the theorem it's using.
That's precisely the critique. They just assert that 4 initial passes are enough to get close enough to the fixed point for the IFT shortcut to be valid.
Hold on, maybe that's okay. I mean, getting 384 layers of effective depth is a huge advantage, isn't it? Even if the gradient calculation is a bit approximate, maybe the sheer computational depth gained outweighs the slight inaccuracy in the gradient direction. Couldn't that be a valid trade-off?
That would be a reasonable engineering argument if the approximation was actually close in practice. The problem is the TRM authors looked closely at the empirical reality inside HRM, even using the examples from the original HRM paper where they used more steps, like 1N7 and OA7 adds to 1N5.
And what do they find? Did the state actually converge?
Not really, no. They found significant empirical flaws that directly contradict the fixed point assumption.
Okay, let's detail those flaws. This is the crucial evidence.
First, they measured the residual error for $7. The residual is basically the difference between the input and output of the function at the supposed fixed point. It measures how far you are from true equilibrium. Ideally, it should be 0. They found the residual for $2 remained clearly well above 0 at every step.
Well above 0. So Sitter-Browler definitely hadn't settled. The high-level state was still changing.
Correct. The fixed point assumption for Zittauer was demonstrably false.
What about Zittauer's, the reasoning state?
Similar story. They found the residual for Zittauer's was also significantly above 0, even after the initial warm-up iterations. And maybe even more damning. Remember that the one-step gradient relies on the state being near equilibrium at the start of the gradient track steps. Step 5 for Zilli. The empirical data showed that Zittauer's was actually very far from converged at that specific critical point.
Wow. So the entire justification for HRM's memory efficiency, this one-step gradient trick based on the IFT, is built on shaky ground. The model achieves massive theoretical depth and saves memory by assuming a state of convergence that empirically just doesn't happen with the number of steps they actually run.
Precisely. The necessary condition for the mathematical shortcut isn't met in practice under HRM's typical operating parameters. This lack of rigor in the gradient calculation, the TRM authors argue, ultimately limits HRM's performance potential. HRM chose efficiency over gradient accuracy.
And TRM, we'll see, makes the opposite choice.
Fascinating. Okay, so the IFT justification is weak, but HRM had another trick for efficiency, didn't it? Section 2.2 mentions adaptive computational time. ACT. This seems like a way to speed up training, but the TRM paper found a hidden cost here too.
Yes, ACT is really important for making HRM practical to train. Remember those Mind All Text 16.7 maximum deep supervision steps? Running all 16 steps for every single training example would be incredibly slow.
Right, most examples probably don't need all 16 steps to get the right answer.
Exactly. So ACT introduces a halting mechanism. The model learns to predict, at each step, whether it's confident enough in its current answer to stop or if it needs to continue for another supervision step. On some datasets, like Sudoku-Extreme, this dramatically reduced the average number of steps needed per sample, sometimes down to less than 2, which is a huge speed up in terms of data throughput.
Sounds great. Where's the hidden cost? The cost lies in how the original HRM implemented the learning for this halting policy. They used a Q-learning-like objective, which required evaluating the potential benefit of continuing versus halting.
Okay. And how do you evaluate the benefit of continuing?
Well, you need to know what would happen if you did continue. Referring to the pseudocode structure described, to calculate the loss for the continue action, the algorithm first has to run the main HRM function once to get the current state, prediction, and halting probability. Let's say ZRYQ, ZRMay, X, Z, X.
That's one forward pass.
That's one forward pass, one NFP net forward pass. But then, to figure out the value or reward associated with continuing, the algorithm effectively needs to perform a look ahead. It has to run the HRM function a second time, starting from the state 0, to see what the next state and halting probability would be.
Z, text X, key text X.
Wait, a whole second forward pass, just to decide whether to stop or not. According to the TRM paper's analysis of the HRM ACT loss function, yes, that second forward pass provides the QText value needed to properly calculate the continue loss component using their specific formulation involving text sigmoid Q as we want.
So, to train the halting policy using this Q-learning approach, HRM effectively performs 2 full forward passes, 2 NFP, for every single optimization step during training.
That's the hidden cost the TRM authors highlighted. While ACT makes the training faster per sample on average because fewer NOR steps are used, the actual computational cost per gradient update step is doubled compared to a standard model that just needs 1 forward pass before backpropagation.
It's an efficiency paradox. Faster average time per example, but twice the instantaneous compute cost per update.
Exactly. It speeds up convergence in terms of epochs or samples processed, but slows down the wall clock time per training batch. And TRM saw this as another area ripe for simplification and optimization.
Okay, so we've thoroughly picked apart HRM's weaknesses. The shaky IFT assumption leading to inaccurate gradients, and the hidden 2 NFP cost of its sophisticated ACT mechanism. Now let's see how the tiny recursion model TRM comes in and cleans house, mostly through simplification and a return to rigor. Starting with section 3.1, TRM begins by completely reinterpreting those latent features. See Ombre to Aller and Dollars. No more complex biological analogies.
None at all. TRM takes a much more pragmatic, empirical approach. They basically looked at what ScioBlot were actually doing in practice. The source paper even mentions visualizing the decoded outputs of these features on tasks like Sudoku.
And what did the visualizations show? What were Soroid and Cidiator really representing?
It was quite revealing. They consistently found that Serial, the supposed high-level feature, could be directly decoded into a meaningful, often valid output format. Like, you could decode ZLers and literally see a solved or partially solved Sudoku grid.
So pseudoverses wasn't some abstract state. It was basically the answer itself.
Pretty much. It was the model's current best guess at the solution. So TRM just renamed it Noel. Simple as that. Tier is the current proposed solution.
Okay, makes sense. What about CRA, the low-level feature?
When they tried to decode zeros on its own, it looked like noise. It didn't correspond to any sensible output structure, but clearly it was crucial for the process. Their interpretation was that CRAS was acting like the model's internal scratch pad, the working memory, maybe analogous to a chain of thought, holding the intermediate reasoning steps needed to arrive at the solution, YARO.
So they renamed ZR2.
Yep, they just call it ZR of the latent reasoning feature.
Wow. That's incredibly clarifying. YAR's the answer is the working memory or scratch pad used to get the answer.
Yeah.
It completely demystifies the Fell-FH-Dal split and the biological baggage. Much cleaner.
Much cleaner. And it immediately suggests why you need both features. You need JALers to represent the structured solution you're aiming for, something you can compare to the ground truth. And you need ZRs to hold the context, the history, the how did I get here, information needed to refine YAR intelligently.
Does the paper show that both are necessary?
Absolutely. They did ablation studies, reported in Table 2. If they tried to remove the reasoning feature ZRL and just have the model update the solution based on itself, and the input $6 performance tanked. Similarly, if they tried to force everything into a single latent state as Siebely, getting rid of the explicit solution representation dollars, performance also dropped significantly. For instance, on Sudoku-Extreme, the two-feature TRM got 87.4%, but a version with only a single CETL feature dropped to 71.9%. You really need both the explicit solution structure and the contextual reasoning scratchpad.
Okay, that simpler conceptual model, Joller for solutions, zeros for reasoning, sets the stage for the next big simplification in section 3.2, the TRM architecture itself. One network instead of two, and way fewer parameters.
This is where the tiny in TRM really comes from. It's a radical reduction in complexity. Remember, HRM used two separate four-layer transformer networks, totaling around 27 million parameters in their typical setup.
Right, 27 million.
TRM throws that out. It uses only one core network, which they just call TextNet. And the single TextNet is usually only 2 layers deep, not 4.
One network, 2 layers. How many parameters does that end up being?
Depending on the embedding dimensions and other hyperparameters, it typically lands in the 5 million to 7 million parameter range, a massive reduction from HRM's 27 million.
Okay, but wait. If HRM needed 2 different networks, file on and 5.0, presumably to perform 2 different kinds of updates, low-level reasoning versus high-level solution integration, how can TRM possibly do both jobs with just one small 2-layer network?
This is arguably the most elegant part of the TRM design. They achieve functional differentiation not through separate weights, but through carefully controlling the inputs to the single TextNet function at different stages of the recursion.
So the task changes based on what you feed the network.
Exactly. The single network TextNet is called sequentially to perform 2 distinct updates within each recursion step. 1. First, it performs the latent reasoning update, TextNet XYZTA. To update the reasoning scratchpad, it takes the original embedded input $6, the current solution state, and the previous reasoning state goal as inputs. Including $6 keeps the reasoning grounded in the actual problem being solved.
Okay, updates the scratchpad using everything.
Second, immediately after, it performs the solution refinement update. Notice the difference here. Update the solution seed, it takes the previous solution state dollar and the newly updated reasoning state $7 from step 1 as input. Crucially, it excludes the original problem input, $6 from this step.
Interesting. Why exclude $6 when updating dollars?
The intuition is that the solution refinement should be based purely on the internal reasoning and the current best guess. It forces the model to rely on its generated chain of thought to figure out how to improve the answer rather than just looking back at the raw input sixel again. It encourages a more abstract, internally driven refinement process for the solution itself.
That's incredibly clever. Using the same weights but different input configurations to implicitly define 2 different functional roles, grounding the reasoning in the problem and refining the solution based on the reasoning.
Isn't it? It's architecturally minimal but functionally powerful, and the results back it up. Ablation studies, Table 1 in the source, showed that this single network TRM approach significantly outperformed a version that tried to stick with HRM's separate $5 and $5 networks, even when controlling for other factors. The single net got 87.4% on Sudoku-Extreme, while the 2-network version only got 82.4%. Simpler was better.
Simpler and more effective. Okay, that covers the architecture and the features. Now for arguably the biggest change, the one that addresses HRM's core mathematical weakness. Section 3.3. TRM bypasses the IFT entirely and commits to full backpropagation. No more one-step gradient approximation.
Exactly. This is where TRM really prioritizes mathematical rigor over the computational shortcut HRM took. They acknowledged that HRM's assumption of fixed-point convergence was empirically flawed and likely led to inaccurate gradients, hindering performance.
So what's the alternative? If you don't use the IFT shortcut, how do you get the gradients for a deep recurrent process?
You have to do it the hard way. You actually track the gradients through the entire sequence of operations that you want to learn from. Full backpropagation through time, essentially, but applied strategically.
Okay, let's detail the TRM deep recursion logic using their pseudocode, figure 3, as a guide. How does it work across the total steps? Remember, a full recursion process involves dollar updates to the reasoning 6, followed by 1 update to the solution.
Right. TRM structures the training carefully to balance rigor with memory constraints. Let's use the optimal parameters they found for Sudoku-Extreme as an example. T8, 23 total recursion steps per supervision instance, and 1n latent updates within each step.
Okay, T8 thrallers and N6 5.
The process starts by running the first $T in full recursion steps without tracking gradients. This is similar to HRM's warm-up phase, allowing the internal state's ELers to evolve and refine before learning happens. So since TT33, it runs the full 1n+1 Eller sequence twice, gradient-free. The pseudocode looks something like this, with torch.agrad for j in range, t-1, and yz equals latent recursion xyz.
Okay, so 2 full passes, each involving one n66 out updates and one yay update, happen just to get the state ready. No gradients stored yet.
Correct. Then comes the crucial part. The final single recursion process, the big one, is executed with full backpropagation enabled, xyz RDCN. This time, gradients are tracked.
And how many operations does that final latent recursion involve when n is 6 to the 67?
It involves $1 plus 1 equals 6 plus 1 plus 1 equals 7 to 7 sequential function calls to the core TextNet. 6 times to update $7 and 1 final time to update yallers. The gradients are calculated and stored for all 7 of those calls in that final sequence.
So the backpropagation path goes through the entire chain of 7 network evaluations in that last step.
Yes, that's the key difference. Instead of approximating the gradient based on just the last 1 or 2 evaluations like HRM did, steps 5 and 6 in our earlier example, TRM calculates the true gradient by unrolling and backpropagating through that entire final $1 plus $1 sequence.
What's the mathematical implication of doing that?
The implication is huge: accurate gradients. By avoiding the IFT shortcut and its unmet assumptions, and instead directly calculating the gradient through the full sequence responsible for the final prediction, TRM guarantees that the weight updates are based on a mathematically sound signal reflecting the actual computation performed. It replaces a potentially noisy, biased gradient approximation with the true gradient for that final decisive step.
And does this mathematical rigor translate to better performance?
Massively so. The paper includes a critical ablation study directly comparing the 2 gradient approaches within the TRM framework. When they used the flawed one-step gradient approximation, mimicking HRM's approach, accuracy on Sudoku-Extreme was only 56.5%.
56.5%.
When they switched to their proposed method, full backpropagation, through the final $1 plus Aller steps, accuracy jumped dramatically to 87.4%.
Wow. From 56% to 87%. That's definitive proof. The accurate gradient calculation is incredibly important.
It really is. It shows that the shortcut HRM took, while saving memory, came at a severe cost to learning effectiveness, at least on these hard tasks.
But wait, full backpropagation through $1 plus 1 equals 77 steps.
Yeah.
Doesn't that bring back the memory problem that HRM was trying to avoid? The paper mentions out-of-memory OOM errors.
It does, and that's the trade-off TRM explicitly makes. Because the model now has to store the activations for that entire sequence of $1 plus $1 steps during the final recursion phase to allow for backpropagation, the memory usage during that phase scales directly with known dollars.
So you can't just make that arbitrarily large.
Exactly. If you increase no more reasoning steps per cycle, or T or more total cycles, too much, you will run out of GPU memory. The paper notes that trying configurations like 1 and 6 lullers TT60s, which would imply an effective depth of 156 layers using TRM's calculation, resulted in OM errors.
So they had to find a sweet spot.
They did. They found that T83 and NA60s provided the best balance. It pushed the reasoning depth as far as possible within memory limits for TTA3, delivering that huge 87.4% accuracy. The paper literally says the memory cost of this full backprop approach is well worth its price in gold, because the performance gain from the accurate gradients is so substantial. They chose rigor, paid the memory price for it during that final step, and reaped the performance benefits.
That makes perfect sense. Prioritize the correct signal, even if it costs more memory for that final step. Okay, section 4 delves into the ablation studies, showing how TRM systematically optimize things. Let's start with 4.1, the really interesting finding about network capacity. Why did reducing the size of the network, fewer layers, fewer parameters, actually improve generalization? That seems backward.
It does seem backward if you're used to the bigger is better LLM world, right? But it makes perfect sense when you consider the training data for these benchmarks.
How so?
These reasoning tasks, Sudoku-Extreme, ARC, AGI, they don't have massive data sets like the web-scale corpora used for LLMs. You typically only have maybe 1,000 or a few thousand training examples.
Okay, relatively small data.
Very small data, and when you have a high-capacity model, lots of parameters, trained on very little data, what happens?
Overfitting. It just memorizes the training set.
Exactly. Massive overfitting. The model learns the specific answers in the training data perfectly but completely fails to generalize the underlying rules or algorithms to new, unseen puzzles.
And the ablation study on the number of layers in the net function showed this clearly.
Crystal clear. They compared using a 4-layer transformer for the core net versus a 2-layer one. The 4-layer version, more parameters, higher capacity, only achieved 79.5% accuracy on Sudoku-Extreme. When they cut the layers down to 2, reducing capacity, accuracy jumped significantly to the optimal 87.4%.
So fewer parameters led to better generalization because it reduced overfitting on the small data set.
Precisely. The key insight here is how TRM allocates its complexity budget. It uses the recursion, controlled by Nomia dollars, and the deep supervision to achieve massive effective computational depth, 42 steps, in their optimal Sudoku config. N-second TC 3000 plus output gives $6 plus 1 3 layers. $732, $42, $2, 222, 10, 31. Let's recheck TRM's depth calc. They define depth differently, just based on the final step. That doesn't split 1 in layers? No. Table 3 suggests $2 less 1 in layers. Let's stick to the concept. Anyway, it achieves this high effective depth, representing many reasoning steps. But crucially, it does this using a network with a tiny parameter count, just 2 layers, 577M params. This combination allows the model to perform complex multi-step reasoning while minimizing the risk of simply memorizing the small training set.
That's a brilliant trade-off. It's like the model's knowledge parameters is kept minimal to force generalization, but its processing power, recursive steps, is maximized to allow complex problem solving. Spend the budget on the process, not the static memory.
Exactly. Focus intelligence on the computation sequence, not just parameter storage.
Okay, moving to section 4.2, let's compare the final optimized recursion parameters between HRM and TRM because this also tells a story.
Right. The paper provides these comparisons. Table 3. Optimized HRM with its less accurate gradients found its best performance on Sudoku-Extreme using TT3 and LIAN33.
Okay, TT3 LAN39, what depth does that correspond to in HRM terms?
Right.
Layers n plus 1t, NEM43 plus 13 joules, 48 effective layers, ignoring an asymptotic comparison. And the accuracy was?
Accuracy for HRM at TTRM $83 was 61.6%.
61.6%. Okay, now what about TRM?
TRM, benefiting from its accurate gradients via full backpropagation, found its peak performance at T3RM but with 9 decibs.
2 3RMs and 666 orders. Same number of cycles, but twice as many reasoning steps per cycle. What's the effective depth using TRM's likely calculation? Maybe TRNs plus 1 in layers with on layers. That would be 3 through 7s plus VRs. 3 through plus 72 equals 42 effective layers. And the accuracy?
The accuracy for TRM at T3 3 was that winning 87.4%.
Interesting. So HRM needed slightly more theoretical effective depth, 48 versus 42, but performed much worse, 61.6%, because its gradients were approximate. TRM achieved much higher accuracy, 87.4%, with slightly less theoretical depth, but benefited massively from having perfectly accurate gradient for its final learning step.
It really highlights that the quality of the gradient signal ensured by TRM's rigorous backpropagation seems more important for effective learning than just maximizing the raw theoretical effective depth number, especially when that number relies on flawed assumptions like HRMs did.
Quality over quantity, even in effective depth. Makes sense. Okay, section 4.3 discusses further efficiency improvements. TRM simplified that ACT mechanism, getting rid of the hidden 2 NFP costs we talked about.
Yeah, this is another nice cleanup. Remember, HRM's complex Q learning style ACT loss needed that second forward pass to NFP to calculate the MathCal-L term.
Right, the look-ahead pass.
TRM basically said, do we really need that complexity? They tested a much simpler ACT mechanism. They completely removed the continue loss component.
So how did it decide whether to halt or continue then?
It used only a simple binary cross-entropy, BCE, loss based on the halt decision. Essentially, at each step, $, it predicts a halting probability P lower. The loss encourages halting P high if the current prediction is already correct, and encourages continuing low if it's not. It doesn't need to explicitly calculate the value of continuing using a look-ahead.
Just a direct signal, stop if you're right, otherwise keep going.
Pretty much. And because it doesn't need the look-ahead, it doesn't need the second forward pass.
So it gets back to the standard 1 NFP per optimization step.
Exactly. It cuts the per-update compute cost in half compared to HRM's ACT.
And did this simplification hurt performance? Usually, simpler heuristics perform worse than optimized Q learning.
Surprisingly, no. In fact, the performance slightly improved. The paper notes that the simplified 1 NFP AC2 mechanism took the accuracy from 86.1% achieved with a more complex setup up to the final 87.4%.
Wow. So the fancy Q-learning ACT in HRM wasn't just costly, it might have even been slightly suboptimal compared to a simpler BCE halt loss.
It seems that way, at least in this context. It proves that the complexity and the 2 NFP cost of HRM's approach were unnecessary computational overhead that didn't actually buy better performance and might have even hindered it slightly. Simpler was, again, better.
Okay, one last stability trick mentioned in 4.3, using an exponential moving average, EMA, on the model weights. Why was this so important, especially for these tiny models on small data sets?
EMA is a technique often used in training generative models like GANs, but it turns out to be crucial here too. When you're training very small models on very sparse data, the training process can be inherently unstable. The loss landscape might be bumpy, and individual gradient updates can be noisy.
So the model's weights can jump around erratically.
Exactly. You can get these sudden, sharp performance drops or even complete training collapse. EMA helps smooth things out. Instead of using the absolute latest weights directly, you maintain a running average of the weights over the last several updates.
How does that help?
It dampens the noise. By using a high smoothing factor, they used 0.999, meaning the average weights are mostly influenced by previous averages, only slightly nudged by the latest update. EMA prevents the model from reacting too violently to outlier batches or noisy gradients. It keeps the weights evolving more smoothly and stably.
And was it critical for TRM?
The ablation suggests it was absolutely vital. They report that without EMA, the best accuracy they could get was 79.9%. Adding EMA with that 0.999 decay factor boosted performance all the way up to the final 87.4% and prevented those sharp collapse events during training. For small models on sparse data, this kind of stabilization is non-negotiable.
Got it. Stabilize the learning trajectory. Okay, let's talk architecture choices in 4.4. This section makes a really important point.
Yeah.
The optimal TRM architecture isn't monolithic. It actually depends heavily on the specifics of the task, particularly the input size or context length, $.
Yes, this is a key nuance. While the core principles of TRM, single small net recursion, full backprop, are general, the specific type of network layer used inside net needs to be adapted to the problem structure.
They compared using standard self-attention layers versus an attention-free approach, right?
Right.
Like MLP mixer.
Exactly. For the Sudoku-Extreme task, the input is a small, fixed-size grid. 1 ollie equals 9 times 9 equals 81, 1. The spatial relationships are local and highly structured.
Okay.
In that scenario, they found that using standard transformer self-attention, which is really designed to capture long-range, complex dependencies and variable length sequences, was actually overkill. It introduced inductive biases that weren't perfectly suited for the fixed grid structure.
So what worked better for Sudoku?
An attention-free architecture inspired by models like MLP Mixer. Instead of self-attention, they used simple multi-layer perceptrons, MLPs, applied independently across the sequence dimension and the feature dimension. This simpler, more locally focused approach proved optimal for the small, fixed Sudoku grid, yielding that best result of 87.4%. They called this version TRM MLP.
Similar MLPs beat attention for the small grid. But what happened when they tried this TRM MLP on tasks with much larger grids, like Maze Hard or ARC-AGI, which used 30 times $30 grids?
It failed spectacularly. The TRM MLP model scored 0.0% accuracy on those larger grid tasks. It completely lacked the ability to generalize its reasoning across the much larger context length, $900.
Wow, 0.0%.
Yeah.
So what did work for the larger grids?
For the larger, more complex grids, they needed the power of self-attention. The version using standard attention layers, which they called TRM-AT, scored 85.3% on Maze Hard.
That's a night and day difference. 85% with attention, 0% without.
It really highlights the importance of architectural choice matching the input structure. The core TRM philosophy, tiny, recursive, rigorous holds, but the specific layer type matters. If the context length lotters is large and potentially variable, the inductive biases of self-attention designed for capturing long-range dependencies are essential for generalization. If dollars is small and fixed, the simpler, potentially more parameter-efficient MLP-based approach won't be better. You have to pick the right tool for the job.
It's perfect sense. Tailor the components. Okay, finally, section 4.5 summarizes the overall results. Let's put the best TRM variant head-to-head against HRM and the LLM giants on those ARC-AGI benchmarks, tables 4 and 5.
Right. Let's look at the optimized TRM app model, which used attention and had about 7 million parameters. We compare it first against its predecessor, HRM, which had 27 million parameters.
Okay, TRM at 7M versus HRM 27.
On the standard ARC-AGI 1 benchmark subset, TRM-AT achieved 44.6% accuracy, HRM scored 40.3%.
So TRM is better and with fewer parameters.
Significantly better, yeah. And on the harder ARC-AGI2 subset, the gap widened. TRMAT got 7.8%, while HRM only managed 5.0%.
Again, TRM wins nearly 3 percentage points higher on a very hard task with roughly a quarter of the parameters. That's impressive.
It really is. It shows the benefit of TRM's architectural simplifications and mathematical rigor over HRM's approach.
For the comparison against the LLMs, how did the 7M parameter TRMAT stack up against models with hundreds of billions of parameters?
This is where the efficiency argument becomes astronomical. Let's take DeepSeek R1, reported at 67 billion parameters.
Okay, 67 billion.
On ARC-AGI1, DeepSeek R1 scored 15.8%.
15.8%. And TRMAT?
44.6%.
So the 7 million parameter TRM absolutely crushes the 67 billion parameter LLM on this reasoning task. It's not even close.
Not even close. Nearly 3 times the accuracy with less than 0.011% of the parameters. Let's look at Gemini 2.5 Pro. The paper cites its score on ARC-AGI1 as 37.0%.
Okay, 37.0%. Better than DeepSeek, but still.
Still significantly lower than TRMAT's 44.6%. Again, a model likely orders of magnitude larger in parameter count is outperformed by the tiny specialized TRM on this benchmark.
The conclusion seems inescapable. For these specific kinds of challenging, supervised algorithmic reasoning tasks, disciplined architectural design focusing on deep, rigorous recursion is far more effective and vastly more parameter efficient than just scaling up general-purpose LLMs.
That's exactly the takeaway. TRM demonstrates that state-of-the-art results in this domain can be achieved not by brute force scale, but by intelligence in design. Simplification, mathematical soundness in the recursion, and careful tuning of components like network depth and layer type to match the data and task. #tag outro.
Okay, let's try to synthesize all of this. We've gone from the brittle nature of LLMs through the clever but flawed HRM to the elegant simplicity and rigor of TRM. For you, the listener, trying to make sense of the AI landscape, what's the core message here? What does this deep dive into TRM really tell us about the future of AI reasoning?
I think the primary takeaway is a powerful validation of structured, iterative computation for problem solving. It suggests that achieving superior performance on tasks that require genuine multi-step algorithmic reasoning might not depend on simply scaling up parameters indefinitely or relying on complex, maybe biologically inspired but mathematically questionable shortcuts like HRM did.
Instead, it depends on...
It depends on rigorously improving the quality and depth of the reasoning process itself, step by step, over time. TRM showed us that by simplifying the architecture radically, one small net, minimizing parameters to fight overfitting on scarce data, and critically ensuring the learning signal is accurate through full, mathematically sound backpropagation, you get much better generalization, stability, and ultimately performance on these tasks.
It's like a triumph of algorithmic process over sheer statistical scale or memory capacity.
Exactly. It suggests the computation budget might be better spent executing a longer sequence of high-quality, focused reasoning steps, rather than just storing slightly more information in a massive parameter matrix.
Moving from, like, a vast, disorganized library, the LLM, to a small, incredibly precise instruction manual that gets executed flawlessly, the TRM.
That's a nice analogy, and it raises a really interesting, deeper question that this research doesn't fully answer yet. Why, fundamentally, is this kind of deep recursion so effective compared to, say, just building a non-recurrent feed-forward network with an equivalent number of layers or parameters?
Right. We talked about the overfitting hypothesis. Fewer parameters generalize better on small data. But is there something inherent in the recursive structure itself, the iterative refinement, that's particularly well-suited for these kinds of problems?
That's the million-dollar question. The iterative nature, the reuse of the same weights, like in net, might enforce a kind of consistency or algorithmic regularity that's harder to achieve in a giant feed-forward model. But it's still an open area.
And that leads perfectly into our final provocative thought for you, the listener, to chew on. TRM, as presented here, is a supervised, deterministic model. You give it a puzzle, it computes iteratively, and gives you one final high-quality answer. But the dominant force in AI right now is generative models, LLMs, that create text, images, code. Could the core principles of TRM, tiny scale, architectural simplicity, deep and rigorous recursion, be successfully adapted or extended to generative tasks?
That's the frontier, isn't it? Imagine a language model where generating each word isn't just the result of one pass through a massive transformer, but the outcome of, say, 42 steps of internal, mathematically rigorous, recursive refinement using a much smaller core network.
Could that lead to more coherent, logical, and perhaps vastly more efficient generative models in the future? applying this less is more philosophy, this focus on structured recursion, to the creative chaos of generation.
It's a fascinating possibility. It would fundamentally challenge the current paradigm that believes only massive scale can unlock complex, high-quality generation. It's the next big question for this line of research.
Something for all of us to think about. Well, this has been a truly deep dive into the nuts and bolts of these tiny recursive models. Thank you for joining us and navigating the details.
My pleasure. It's fascinating work.
We hope this gave you the detailed, rigorous understanding you were looking for. Until next time on the deep dive, keep digging deeper. Welcome to the Deep Dive, your shortcut to getting instantly well-informed on some pretty complex topics.
Glad to be here.
Today, we're really digging into neural network architecture. Specifically, there's this fascinating new research that seems to push back hard on a core idea in AI right now.
Yeah, it really challenges that bigger is always better mantra, doesn't it?
Exactly. That whole scaling paradigm that's dominated deep learning for, what, the last 5-6 years?
Pretty much. You know, the standard playbook. If your model isn't working, throw more parameters at it, scale up the training data, pour in more compute. It's been the default.
Right. But this paper we're looking at today, it's called Less is More: Recursive Reasoning with Tiny Networks. It flips that script. It suggests, well, it provides pretty solid evidence, actually, that smart architecture and being really careful with the math can beat raw size, at least for certain kinds of problems.
Especially these complex sort of logical reasoning tasks, that's where this really shines.
Okay, so let's hit the listener with the headline finding right away, because honestly, it sounds almost unbelievable without the context.
Go for it.
We're talking about models called tiny recursive models, TRMs. And when they say tiny, they mean tiny, like as few as 7 million parameters.
Yeah, 7 million. It's almost nothing in today's world. You think about something like GPT-3.
That's 175 billion, right?
Exactly. So this TRM, it's what, like 0.004% of the size, maybe even less, depending on the exact LLM you compare it to. It's minuscule.
Okay, 7 million parameters.
And yet, these tiny TRMs are outperforming the giants. On really hard deterministic puzzle benchmarks, think things like the abstract reasoning corpus, ARC-AGI, they're getting higher accuracy than massive cutting-edge models. We're talking models like Gemini 2.5 Pro, DeepSeek R1.
Models with hundreds of billions, maybe trillions of parameters.
Right. And the TRMs are beating them using, as the paper states, less than 0.01% of the parameters. It's a bit of a shock to the system.
It really is. A true David and Goliath situation in AI engineering. So our mission today for this deep dive is to go beyond just saying, wow, look at those accuracy numbers. We need to get under the hood.
Exactly. We need to unpack the mechanics. How does this work? What did they change architecturally?
And specifically, we want to compare this TRM directly against the model that came before it, the hierarchical reasoning model, or HRM. Because understanding HRM's limitations is key to seeing why TRM is such a breakthrough.
Absolutely. HRM laid the groundwork, but TRM identified the weaknesses and simplified things dramatically.
And we're going to get into the weeds here. We'll focus on the notation, the specific mathematical logic, the derivations. Basically show exactly how this simplification didn't just make the model smaller, but actually made it generalize better.
That's the plan. Rigorous, step by step.
Okay, let's set the stage. Why are we even talking about specialized reasoning models? Why can't these giant large language models, the ones that are so amazing at writing emails or, summarizing text, why do they fall down on these hard logical puzzles, things like Sudoku or these abstract spatial reasoning tests?
Yeah, it seems weird, right? They understand language, they can generate complex text, but ask them to follow strict rules step by step, and they often stumble.
What's the core reason for that?
It really boils down to their fundamental architecture. LLMs are typically autoregressive, meaning they generate output one piece at a time, one token, usually a word or part of a word based on all the pieces that came before it. It predicts the most likely next token, adds it, then predicts the next one, and so on.
Okay, like finishing a sentence.
Exactly. But think about Sudoku. You put a number in a cell. Let's say the LLM predicts a 5. Then it predicts the next number based on that 5 being there. But what if that 5 was wrong, violated the Sudoku rules?
Ah, I see. Everything that comes after that wrong 5 is now built on a faulty foundation.
Precisely. The entire chain of reasoning, the entire solution gets invalidated by that single early mistake. There's no built-in way for the standard LLM architecture to easily backtrack and say, oops, that 5 was wrong, let me try 6 instead and recalculate everything.
So the process is incredibly brittle for these kinds of rule-based problems. One slip and the whole thing collapses.
Highly brittle, non-robust. It's just not what they were originally designed for, this kind of constrained, iterative, backtracking logic.
Okay, but the big companies know this, right? They've tried to patch it up. You mentioned chain of thought.
Right, chain of thought, or CoOT, is a common technique. The idea is you prompt the LLM to essentially think out loud first, generate a step-by-step reasoning process, like a little scratch pad, before it gives the final answer.
And does that help?
It definitely improves accuracy on many reasoning tasks, yeah.
Yeah.
But the paper points out it's not a perfect fix, more like a bandage.
Why not? What are the downsides?
Well, first, it's computationally more expensive, especially at inference time. You're generating 2 sequences now, the reasoning steps and the final answer. That takes more time in compute.
Okay, makes sense.
Second, you need really high-quality training data that includes these reasoning steps. And that kind of detailed step-by-step reasoning data is often hard to come by. It's scarce and expensive to create.
Right.
And third, it's still potentially fragile. What if the reasoning trace itself has a mistake in it? If the LLM makes a logical error in its thinking out loud part, that error is just going to propagate into the final answer anyway. The brittleness hasn't fundamentally gone away.
So CoT helps, but doesn't solve the core autoregressive problem. What about the other technique, TTC, test time compute?
Ah, TTC. That's more of a brute force approach.
Yeah.
You basically run the model multiple times, maybe with slightly different settings or just asking for multiple outputs.
Like getting a second opinion. Or many opinions.
Kinda, yeah. You generate, say, different potential answers or reasoning paths. Then you use some method, maybe a majority vote, or picking the answer the model seemed most confident about to choose the final result.
So hoping that the correct answer appears more often or with higher confidence among the multiple tries.
Exactly. Models like Gemini 2.5 Pro reportedly use techniques like this on benchmarks. But the downside is obvious. It's incredibly compute intensive. If you need to run the model, say, 10 times to get one decent answer, you've just increased your inference cost by a factor of 10.
Oof. Okay, so even with these patches, Kate, adding complexity and needing special data, TTC just burning massive amounts of compute, that giant LLMs still struggle with the really hard reasoning tasks.
That's the crucial point the TRM paper makes. They cite this specific data point. Even with all these techniques, a model like Gemini 2.5 Pro apparently only managed about 4.9% test accuracy on this benchmark called ARC-AGR2.
4.9%. That's barely better than random guessing on a complex task.
It's very low. And it highlights that there's this fundamental gap. These general-purpose LLMs, despite their scale, just aren't suited for certain types of specialized, high-precision, iterative reasoning.
Which creates the opening for something different.
Exactly. And that something different, the first real breakthrough in this direction, was the hierarchical reasoning model, HRM. This was work by Wang and colleagues.
Okay, so HRM came before TRM. What was its big idea?
HRM was designed specifically for these kinds of tasks: Sudoku, maze solving, ARC-AGI. It was a supervised learning model, meaning it was trained on examples with known correct answers, unlike some LLMs. And it introduced 2 really novel concepts.
What were they?
The first was this idea of recursive hierarchical reasoning.
Okay, let's break that down. Recursive, hierarchical.
Yeah, the core was using recursion, feeding the output of the model back into itself repeatedly, but doing it through 2 distinct smaller networks. Not one big one, but 2 specialized ones.
And that works. Why too?
They called them 5-hours and 5-hours. The idea, or at least the original justification, was that they operated at different conceptual frequencies.
Frequencies. Like brainwaves.
Kinda, yeah. That was the biological metaphor they used. 5-hours was the low-frequency network, and 5-hours was the high-frequency one. Now, we should say up front, the TRM paper later argues this metaphor isn't really necessary or maybe even accurate, but that was the initial HRM concept.
Okay, so 5 and dollars. We need to be really clear on the notation here, especially if we're going to critique it later. How did they interact? What do they actually do?
Right. So each network takes inputs and produces an output, a sort of internal representation or latent feature.
Okay.
The low-frequency network, $5, its job was to output the high-level feature, which they call $. You can think of $$ as representing the overall state, maybe the current guess at the whole Sudoku board, the big picture solution state.
Okay. Fate operates, high-level solution. What about $?
The FATE, the high-frequency network, did the opposite. It output the low-level feature, sec dollars. And sec dollars was meant to represent the more detailed, fine-grained reasoning, the context, the step-by-step process, maybe the internal scratchpad work needed to arrive at the solution, sec dollars.
Interesting. So 5 to Zexto, solution, 5H to Zekadol, reasoning context. How did they connect?
This is key. During the recursive loop, both of these latent features, secadollar and zegeprudol, were fed back as inputs into both networks on the next step. Ah, okay. So $5 took both dollars and Celeste, plus the original input problem, to update Celeste.
Well, actually, $5 updated Celeste, and 5 updated. Let me rephrase that for clarity based on the original formulas. Okay, checking the specific flow. Yes, $5 takes Celeste and the input Celeste to produce the new Celeste. And $5 takes the current Celo Wiener to produce the new Celeste. My apologies, it's easy to mix up the indices.
No problem. So 5L, ZH is less to ZLS to ZLH to ZHH to ZH, ZH. That interdependence is the core of the hierarchical part.
Exactly. The low-level reasoning depends on the current solution guess, and the solution guess depends on the current reasoning state. They're refined together recursively. That was novelty 1.
Okay, clear. What was the second novelty?
The second one was called deep supervision. This was their trick to simulate having a massively deep network without actually running out of memory.
Right, because deep networks are memory hogs, especially during training when you need to store activations for backpropagation. Precisely. So deep supervision involved running this recursive $5 update process multiple times, let's say for Nana steps. In the HRM paper, Nana could be up to 16. Each step aims to improve the answer.
16 steps of recursion. That sounds like it could get deep.
It does. But here's the clever part, and also the part that TRM critiques later. To make this feasible, HRM reused the latent features from the end of one supervision step as the starting point for the next supervision step.
Okay, like passing the baton.
Yes, but crucially, they did this after detaching those features from the computational graph.
Detaching. What does that mean mathematically or computationally?
It means you tell the automatic differentiation system, okay, use these values, dollars and dollars, to start the next calculation, but don't track gradients back through them to the previous step. You essentially cut the history. In code, it's often represented as something like ZL detach.
Ah, so the gradient calculations for step K plus hours of 1 don't flow back into step taros.
Exactly. This detachment breaks the long chain of dependencies. It acts like a residual connection in a very deep network, allowing information to flow forward, but it prevents the backward pass, the gradient calculation, from having to store activations for all 16 steps simultaneously.
Which would cause an out-of-memory OAM error almost instantly on current hardware.
Absolutely. So detachment was the key memory optimization technique that enabled this deep supervision across many steps. It allowed them to emulate a very, very deep network.
Got it. Detachment saves memory, but as we'll see, might have implications for gradient accuracy. Okay, let's dive into the specific forward pass sequence. You said understanding this trace is crucial. It's section 2.2 in the source paper.
Yes, this detailed sequence explains how HRM combined the recursion, with the detachment for deep supervision, and importantly, where the gradient approximation came in.
First, the input. How's the problem, like the Sudoku grid, represented?
The raw input, let's call it tildes, like the image of the grid, is first processed by an input embedding network, $5. This network, parameterized by SCAT-AI, turns tilde into a tensor set.
A tensor, like a multi-dimensional array.
Exactly. Typically with a shape like Budawal, L, the dollars is the batch size, how many puzzles you process at once. Dollars is the context length, like $9 and times 9 equals 81.1 for a standard Sudoku, and dollars is the embedding dimension, the size of the vector representing each cell or position.
And the original HRM, what kind of network was $5 at $5?
They were all initially designed as 4-layer transformer blocks. Transformers are powerful sequence processors, so it made sense. There was also an output network, and also a 4-layer transformer, to decode the final latent state into the actual answer.
4 networks, 5L, FL, FH, SL, each with 4 layers, okay?
Yeah.
Now, the core recursive loop, HRM used fixed hyperparameters for this part, right?
Yes. Typically N52 for the number of times phi was applied per cycle, and TD2 for the number of full cycles, phi last step, then third step, within a single forward pass before considering the deep supervision steps.
Okay. 1 and 2 tollers, T2 chows. Let's trace the sequence of function calls.
Yeah.
We need to be precise about when gradients are tracked and when they aren't. Assume we have initial ZH and Salar.
Right. So starting the first cycle, T taller.
Update the low-level feature CL arrow left arrow, FL, CL plus CH plus X. This addition, CL plus CH plus X, combines the previous state and the input problem. Crucially, this is done without gradients. No history is stored.
Okay, first valid call, no gradients.
Step 2. Apply 5-LL again, because that's the left arrow, FL, CL plus ZH plus XDOL. Still without gradients. We've now done the 2 fuller steps for the first cycle.
2 valid calls done. What's next in the cycle?
Step 3. Bait the high-level feature CLRL using the newly refined CL left H, CL plus CH. This completes the first full cycle. And importantly, this step is also performed without gradients.
Okay, so the entire first cycle, steps 1, 2, 3, is purely feed-forward, just updating the state, no preparation for backpropagation yet. Now we start the second cycle, T22.
Exactly. Step 4. Begin the second cycle by updating ZL again. ZL again. ZEV left arrow, FL, ZL plus ZH plus XR. Now here's where things get a bit subtle regarding the memory optimization. Often, before starting the steps where gradients will be tracked, an explicit detach operation might happen here, or just before step 5, ZL left arrow ZL and ZL attach left arrow ZH. This ensures absolutely no gradient path exists back to the first cycle, steps 1 to 3. Let's assume that happens. So step 4 itself is still without gradients.
Right. So the first 4 function calls, 2 4 on 1 4 another dollar, all untracked. This is purely about getting the latent state's cell emit array to a better place before the optimization part starts.
Precisely. Now comes the part that relies on the approximation we'll critique later. The HRM model assumes that after these 4 steps, the system is close enough to some ideal state to start tracking gradients just for the very last bit.
Okay, so step 5 is the first one where gradients matter.
Step 5. Update ZLLers one more time, completing the into 2 steps for the second cycle. ZLL and left arrow FL, ZL plus ZH plus XLO. This step is performed with gradients. The system starts building the computational graph here, storing information needed for backpropagation.
Finally, the gradient tracking starts only on step 5 out of 6 total calls so far.
Correct. And then step 6, the final update to the high-level feature, ZLRs left arrow FH, ZL plus ZH. This is the very last step in the T2 taller into 2 sequence. It's also calculated with gradients.
So to summarize the sequence, NT2 dollars no grad, 5H stellars no grad, 5H no grad, 5H nullers no grad, then 5H2 dollars, each dollars no grads, and 5H stellars and telegrad, then 5H is with grad, 5 dollar with grad. Only the last 2 out of 6 calls actually contribute to the gradient calculation for the optimizer.
Exactly. And finally, the prediction is made by feeding the final deputies through the output network. Left arrow text argmax, this adder is the model's predicted answer, like the completed Sudoku grid.
This memory-saving trick, only backpropagating through the last 2 steps, is what allowed them to claim that massive effective depth. Let's calculate that again explicitly using their formula.
Right, the formula they used was text effective depth times n plus 1 times t times n text.
Okay, let's plug in the typical HRM values. Text layers was 4 since 4 on hour and next was for 4-layer transformers.
Yep, text layers was 2, the number of 4 nulls per cycle. So n plus 1 is 3, representing 1 full cycle's worth of network applications. 4 nuller FL, FH2.
Correct, n plus 1, 33.
$2 was 2, the number of cycles in 1 forward pass before deep supervision.
T22.
And none to 6 was the maximum number of deep supervision steps, which was 16.
6 of depth, 4 times 2 plus 1 times 2 times 1621. And that's $4, 3 times 2 times 1670.
Which equals $12 times 32 equals $12 times 32 equals 384 too.
384 effective layers. That's how HRM created this illusion of a very deep network using relatively small components, Buffalo SFH2, and this deep supervision trick.
Exactly. But the entire feasibility, the entire justification for claiming this depth is meaningful rests squarely on the assumption that tracking gradients through only those last 2 steps, step 5 and 6, is a good enough approximation for the gradient you would have gotten if you tracked it through all 384 effective layers.
And that assumption is where the problems begin, according to the TRM authors. Right, this brings us squarely to the critique. That one-step gradient approximation tracking only the last 2 steps, it sounds efficient, saved a ton of memory, enabled the 384 effective layers. But it depends on some heavy mathematical machinery, doesn't it?
It does. The theoretical justification HRM leaned on is the implicit function theorem, or IFT.
IFT. I've heard that mentioned in the context of other advanced models, like deep equilibrium models, DEQs.
Exactly. DEQs are models designed explicitly to leverage the IFT. The theorem basically says that if you have a recurrent function that converges to a stable fixed point, you can calculate the gradient at that fixed point without needing to differentiate through all the steps it took to get there. It's a powerful shortcut.
Okay, converges to a stable fixed point. Let's define that rigorously for the HRM case. With VLR, what does that mean?
It means that if you keep applying the recursive updates over and over. Eventually, the latent states ZLR and CLR should have stopped changing. They reach an equilibrium. Let's call these fixed point states CLevers and ZH.
So applying the functions again wouldn't change the result?
Pretty much, yes.
All right.
But mathematically, the fixed point condition is that the state CLLEH satisfies these equations, at least approximately. CL prox FL, CL plus CH plus X, CL reference prox FL, CL plus X, FH, ZL plus CH. If and only if the system has actually reached this stable state, COA, then the IFT provides a way to calculate the gradient using just one more step, which is what HRM tried to approximate with its step 5 and 6 tracking.
Okay, the condition is convergence to ZL. So what's the problem? Why is HRM's application of this questionable?
The fundamental flaw identified by the TRM authors is that HRM doesn't actually ensure convergence. It just stops after a few steps and assumes it's close enough.
Wait, so unlike those DEQ models you mentioned, which presumably have some mechanism to check for convergence...
Right. DEQs typically use iterative methods, like root-finding algorithms, and they keep iterating until the difference between the current state and the next state, the residual, is incredibly small, below some tolerance threshold. They actively solve for the fixed point symbol.
But HRM doesn't do that.
No. As we traced, HRM just runs its fixed sequence. Cyvalar, Cyvalar, no-grad, Cyvalar is no-grad, Valar no-grad. That's only 4 untracked function calls. Then it immediately jumps into the gradient tracking step, step 5 and 6, implicitly assuming that those first 4 steps were sufficient to reach the fixed point symbol.
It assumes convergence without verifying it.
Precisely. It applies the IFT shortcut without satisfying the theorem's prerequisite condition.
And is there evidence that convergence wasn't reached after those 4 steps?
Yes. The TRM paper points to empirical evidence, including plots seemingly from the original HRM work itself, that strongly suggests convergence was nowhere near being met.
What did that evidence show?
They highlight a few key things from analyses run with slightly different parameters, like 1N7 task, TQ77, which is even more steps than the standard NE2 TU7ing, but illustrates the point. First, the residual for Z0, the high-level solution state. A plot showed this residual remaining clearly above 0, even after many recursive steps. If the residual isn't near 0, the state is still changing. Cedius has not converged to CHA.
Okay, the solution state was still fluctuating.
Second, the low-level reasoning feature, $7. It seemed to take even longer to stabilize, and its residual was also significantly non-zero when the gradient step would typically occur.
So neither state had settled down.
But the most damning point, arguably, is when the assumption is made. Remember, the gradient tracking starts at step 5, which is an out of call. The IFT approximation effectively assumes the Zollers, and more already at their fixed points before this step begins. But the evidence showed CED was particularly far from converge right after the previous Zoller call. Step 4 in our TOC example. It's making the fixed point assumption at precisely the moment the state is known to be actively evolving.
Wow. Okay, so the mathematical foundation for that memory-saving gradient shortcut seems shaky at best.
Very shaky. It seems HRM achieved its efficiency by using an approximation that wasn't theoretically justified under its actual operating conditions.
And the implication for the listener here is pretty significant, right? If the gradient calculation is based on a faulty assumption,
then the gradients you're using to train the model are likely inaccurate. They don't properly reflect how changes earlier in the recursive process actually affect the final output.
Which would likely limit how well the model can learn complex dependencies and generalize, especially on really hard problems.
Exactly. It hobbles the learning process. This inaccurate gradient signal stemming from the unjustified IFT shortcut is likely a major reason why HRM's performance, while groundbreaking at the time, ultimately plateaued and was surpassed by TRM's more rigorous approach.
Okay, that's a huge critique point. The IFT assumption was flawed. What was the second major weakness TRM identified in HRM? You mentioned something about adaptive computational time.
Yes, ACT, adaptive computational time. This was another seemingly clever optimization in HRM, designed to save compute time during training.
How did it work? It related to those LUN-TEXT 16.6 deep supervision steps, right? Running 16 steps for every single training example sounds slow.
It is very slow.
Yeah.
So ACT was introduced to allow the model to learn to stop early. Instead of always running the full 16 steps, maybe for an easy Sudoku puzzle, the model could learn to halt after, say, 3 steps if it was already confident in the answer.
Okay, that makes sense. It adapts the computation time based on the difficulty of the input. The paper mentions it reduced the average steps to less than 2 on some tasks.
Yeah, on Sudoku-Extreme, the average dropped way down, so it definitely saved time per sample. But, and this is the catch, the mechanism for learning when to halt introduced a significant hidden cost.
A hidden cost. How so?
To learn the optimal halting policy, HRM used a technique related to Q-learning. It needed to predict the value of halting now versus continuing for one more step. This involved calculating two different loss terms.
Okay, let's look at those. There's a halt loss, math calcs halt. That seems straightforward.
Relatively, yes. The model has a little Q head attached, usually processing the high-level state $, which outputs a probability, let's call it $2 bad. Might be the probability that halting now is the best action. The halt loss basically encourages the model to predict halt, make $2 high, if the current answer is already correct compared to the true answer, yes, is true.
So MathCal uses something like binary cross entropy BCE, comparing two ballers to whether the answer is right.
Exactly. It's roughly mathcal text halt, code 2AG on. This part only needs the results from the current forward pass. No problem there.
But there was a continue loss as well.
Yes, and this is where the hidden cost comes in. The continue loss needs to estimate the value of not halting now, i.e. the value of continuing to the next step, step K plus $. To do that properly within the Q-learning framework they used, the model needs to know what the halting probability would be at that next step. It needs Q text next.
Ah, and to calculate to Q text the halting probability at step K plus $, and you actually have to run step K plus $.
Precisely. You have to take the current latent states, CH, from step K,
Yeah.
run them through one full HRM forward pass, all 6 function evaluations,
Wow.
5 at dollars, FL, FH, FL, FL, FHT, to get the states for step K plus $, and then calculate 2 text next using the Q head on ZHA.
Wait, so for every single training step, just to calculate the loss for the ACT mechanism, the model has to run the entire HRM forward pass twice.
Yes, that's the hidden cost. First forward pass, let's call it NFP1, to get the current state, prediction, and halt probability to $. Then a second full forward pass, NFP2, using the results of the first, just to calculate T only needed for the continual loss component, math will continue.
Wow. So while ACT reduced the number of effective steps per sample on average, it doubled the amount of computation required per optimization step during training.
Exactly. It required 2 normal forward passes, 2 NFP per optimizer update. This significantly slows down the overall training throughput, even if individual samples finish faster on average. It's a major, often overlooked computational burden.
Okay, so two big critiques of HRM emerging. A potentially inaccurate gradient due to the flawed IFT approximation, and a surprisingly expensive training process due to the 2 NFP requirement to its ACT mechanism. This sets the stage perfectly for TRM to come in and simplify things. All right, so HRM, despite being a breakthrough, had these issues. Questionable math underpinning the gradients and a hidden cost in its adaptive timing. How did tiny recursion models, TRM, address this? What's the core philosophy behind TRM?
Simplicity and rigor, really. TRM essentially looked at HRM and said, what can we strip away? What complexity isn't pulling its weight? And how can we make the core mechanics mathematically sound?
Okay, where did they start simplifying?
The first thing was reinterpreting those latent features,
Yeah.
telomeres and side pause. They ditched the whole biological low-frequency justification that HRM used.
Which you mentioned earlier felt a bit metaphorical anyway.
Exactly. TRM just looked at what the features were actually doing functionally in the model.
And what was the new interpretation? How did they rename them?
It's much more intuitive. ZRHR, which in HRM was the high-level feature representing the solution state. TRM just calls it way. It is the current proposed solution, the output being iteratively refined, like the Sudoku grid.
Simple enough. ZRH dollar becomes the solution guess. What about ZR dollar?
ZRR, the low-level feature that HRM framed as detailed reasoning. TRM renames it to just ZR. This ZR is the latent reasoning feature, the internal state, the model's scratchpad or internal chain of thought that carries context from step to step.
So Euler is the what, the answer, and ZR is the how, the reasoning context to get there.
That's a great way to put it. And the TRM paper provides some nice visualizations, like in their figure 6, that support this. If you try to decode the old CRs, you often get something that looks like a plausible, maybe partially complete Sudoku grid. But if you try to decode ZR, the old CRR, it usually just looks like noise. It's an internal representation, not meant to be directly interpretable as the solution itself.
Interesting. But if they're simplifying, why keep two features at all? Why not just have one single latent state that represents everything?
They actually tested that. It's a key ablation study in their table too. They tried a version with only a single latent feature.
And what happened?
Performance tanked. On Sudoku-Extreme, accuracy dropped from 87.4% with separate doubblers down to about 71.9% with a single combined doubler.
So a significant drop. Why is that separation so important functionally?
The thinking is that the model needs distinct representations for the thing it's trying to produce. The solution, image, and the internal context or steps it's using to get there, the reasoning, the solver. Forcing both into a single vector cell makes it much harder for the model to perform that iterative refinement process effectively. It muddles the signals. So while the hierarchical frequency story might have been unnecessary, the functional separation between solution state and reasoning context proved essential.
Got it. Keep users, but understand them functionally. Okay, what's the next simplification? This is where the tiny part comes in, right? The parameters.
Yes. This is the most dramatic architectural change. HRM, with its two 4-layer transformer networks, FHTOL, plus input-output networks, clocked in around 27 million parameters.
Okay, 27M for HRM? What about TRM?
TRM slashes this drastically. First, it gets rid of the two separate networks, $5 and 5S.
Yeah.
There's only one core network now, which they just call net.
One network instead of two.
Yep. And second, they reduce the depth of that core network. Instead of 4 layers like in HRM, net typically only has 2 layers.
Whoa. Okay, one network, only 2 layers deep. How many parameters does it end up being?
Depending on the exact configuration, we'll get to attention versus MLP later, TRM comes in at around 5 to 7 million parameters.
So down from 27M to 57M, that's a reduction of what, 75, 80%? That's huge.
It's a massive reduction, and it's only really feasible because they rely on the recursion itself to provide the necessary computational depth rather than packing depth into the network block itself.
But wait, if there's only one network, net, how does it do the two different jobs that Fallen and Hang used to do? How does it know whether to update the reasoning state, say, or the solution state later?
This is actually quite elegant. The single network net implicitly performs different functions based on the specific inputs it receives for each type of update.
Ah, so the inputs tell the network which role to play.
Exactly. There are two distinct update rules. First, the latent reasoning update. Updating first, so the network needs all the available information, the original problem question $, the current solution guessNet, and the previous reasoning state cs.AI. So the call looks like this. First, the latent reasoning update. Updating 6net XYZC.
Okay, includes $6. That makes sense for updating the reasoning based on the problem.
Then second, the solution refinement update. Updating there. For this step, the goal is to refine the solution based only on the current solution and the just updated reasoning context. Critically, the original problem input, $6, is excluded here. The call is cirrus on boat.
Ah, I see. Excluding $6 forces the network to focus solely on refining the solution based on its internal reasoning and its current guess without constantly looking back at the original question during this specific refinement step.
Precisely. It creates a functional separation using the input signature. One network, 2 roles, defined by what you feed it. It's a much cleaner, simpler design than HRM's dual networks.
Very clever. Okay, simpler architecture, fewer parameters. But you said the other pillar was rigor. This relates back to that flawed gradient approximation in HRM.
Absolutely. This is arguably TRM's most significant contribution conceptually. They completely abandoned the implicit function theorem shortcut and the associated fixed point assumption.
They just threw it out.
They recognized that the potential inaccuracies from that approximation were too high a price to pay for the memory savings, especially if the goal was maximum performance and generalization on tough tasks.
So if they're not using the IFT shortcut, what are they doing for gradients? How do they handle the deep recursion without running out of memory?
They opt for the straightforward, mathematically rigorous approach. Full back propagation through the relevant computation combined with the same detachment trick for the deep supervision steps that HRM used, but applied more carefully.
Okay, let's trace the TRM recursion logic, maybe using their pseudocode from Figure 3 as a reference. How does it work step by step, especially concerning gradients?
Right. First, TRM defines a full recursion process differently. It consists of no updates to the reasoning state, $0, followed by 1 update to the solution state night. That's a total of $1 plus dollar calls to the single net function.
So, $, times net, XYI is to update Z, then 1 time net, update is $, that's 1 block.
Exactly. Now let's say they want to run this for $2 within 1 deep supervision step, similar to HRM's dollars, but applied differently. Here's how TRM handles the gradients. 1. For the first TL and unread cycles, the entire sequence of $1 plus $, network calls is run without gradients. This is just for refining the states in $, and dollars, similar to HRM's initial untracked steps. Information flows forward, but no history is kept for backprop.
Okay, so if TT33, the first two full cycles, each involving no updates and one yo update, are run completely detached, untracked.
Correct. 2. Then for the final 12th cycle, the entire sequence of $1 plus $1 network calls, one not updates, one yo update, is run with full backpropagation.
Wait, full backprop through all dollar plus dollar steps in that last cycle, not just the last one or two like HRM?
Exactly. Full backprop through the entire final sequence of computations that produced the output for that supervision step.
Okay, let's plug in some numbers. The paper mentions TRM often found optimal performance around, say, $2 and 1 teller 6 possible.
Yes, those were good parameters for tasks like Sudoku.
So in the final cycle, TRM would backpropagate through $1 plus 1 plus 1 plus 1 plus 1, 77 consecutive calls to the net function.
Correct. 7 steps fully tracked for gradients in that final iteration.
That sounds significantly more memory intensive than HRM's approach, which only tracked the last two steps, 1.515 cal.
It absolutely is more memory intensive during the backward pass. You need to store the activations for all 7 steps in that final sequence. But the crucial difference is the mathematical implication.
Oh, shit.
Because TRM backpropagates through the entire actual sequence of computations that generated the final YI and lollers for that step, the resulting gradient is guaranteed to be mathematically accurate, up to numerical precision. There's no reliance on an unverified fixed point assumption, no IFT shortcut. It's calculating the true gradient of the executed computation.
It's honest about the computation it actually performed.
Exactly, and the empirical results validate this trade-off. The paper shows that switching from HRM's flawed one-step gradient approximation to TRM's full backpropagation, even comparing within the TRM framework itself, was responsible for a massive performance leap. On Sudoku-Extreme, accuracy jumped from around 56.5%, using a one-step gradient simulation within TRM, to the headline 87.4% using full backprop.
Wow, that's a 30-point accuracy gain just from calculating the gradients correctly.
It's huge. It demonstrates that gradient accuracy was paramount. The increased memory cost of tracking those 7 steps instead of 2 was, as the paper puts it, well worth its price in gold.
So the core philosophical shift is clear. HRM prioritized memory efficiency by compromising gradient accuracy via the IFT shortcut. TRM prioritized gradient accuracy by accepting a slightly higher memory cost, though still tiny overall compared to LLMs, and doing the full correct backpropagation. And that rigor led to much better learning and generalization.
That's the central argument. Simplicity in architecture, rigor in the mathematics.
Okay, so TRM's design seems much cleaner and more mathematically sound, but the real proof is in the pudding, right? The ablation studies, where they systematically tested different components, must have revealed some interesting things.
Absolutely. The ablations are where TRM's success story gets really compelling and honestly quite counterintuitive based on standard deep learning wisdom.
Let's start with network capacity, the size of that single net module. We already know they reduced it from HRM's 4 layers to just 2. But did they experiment further? Table 1 in the paper seems to cover this.
Yes. Table 1 looked at the impact of layer count. And the finding was surprising, especially given the trend towards deeper networks elsewhere in AI.
What did they find was optimal?
For tasks like Sudoku-Extreme, where the training data is incredibly scarce, remember only about 1,000 examples?
Right, tiny data set.
They found that using 2 layers in the net module gave the best performance, hitting that 87.4% accuracy.
Okay, 2 layers was best. What happened if they used more layers, like the 4 layers HRM used? Did performance improve further?
No, it actually got worse. When they increased the net module to 4 layers, the accuracy on Sudoku-Extreme dropped significantly, down to 79.5%.
Adding more capacity hurt performance. That goes against the usual scaling laws.
It does, but it makes perfect sense in the context of very limited data. With only 1,000 training examples, a deeper, more complex network like 4 layers has too much capacity. It starts to overfit.
Meaning it just memorizes the answers to the training puzzles instead of learning the underlying rules of Sudoku.
Exactly. It learns the training set perfectly, but fails to generalize to new, unseen puzzles. The smaller 2-layer network, despite having less raw capacity per block, strikes a better balance. It has enough capacity to learn the reasoning steps when combined with the deep recursion, but not so much capacity that it easily overfits the tiny dataset.
So the hypothesis is the deep recursion, like the T62 rounds and Ingo6 giving $7 times 16 approx 112 effective steps if we extend the logic, though the paper calculates it slightly differently, maybe on times n plus 1 giving $16 times 7 sums 112, provides the necessary computational depth, while the tiny parameter count, 5M in the 2-layer MLP version, acts as a crucial regularizer, preventing overfitting on scarce data.
That seems to be the key insight. Depth comes from recursion, generalization comes from architectural minimalism.
Fascinating. Okay, what about optimizing the recursion parameters themselves?
Oh,
To the number of cycles and the number of Z updates per cycle. Table 3 compares HRM and TRM here.
right. This table shows how the different gradient strategies affected the optimal recursion depth.
What did HRM need with its flawed one-step gradient?
When HRM was optimized using its own framework, the best results, around 61.6% on Sudoku-Extreme, were achieved with 2 and 3.3 and 3.3 verts.
Okay, T3 and he's 3.3 for HRM. How deep is that effectively? Using their old formula's logic, layers n plus 1t. If one layer is $3, that's $4. 3 plus 1 times 3 is 4 times 4 times 3 enters 48 effective layers per supervision step.
Roughly, yes, by that calculation. Depth 48 gave HRM its peak.
Now what about TRM with its full backpropagation? What T-nanometers worked best there?
TRM achieved its much higher 87.4% accuracy with T33 and a solve 3 ers.
Under $3. NSX $700, so the number of cycles stayed the same, but the number of Z updates, $9, doubled from 3 to 6. What's the effective depth there?
With no layers, $2 for TRM, $2 times 6 plus 1 times 3 times 7 times 3 equals 42 effective layers per supervision step.
Using that same logic, yes, around 42 layers. It's interesting the effective depth per step is actually slightly less than HRM's optimal, 42 versus 48, but the performance is vastly superior. Which reinforces the idea that it's not just about effective depth, but about the quality of the learning signal, the accuracy of the gradients.
Precisely. But there's a trade-off highlighted here too.
Which is?
The memory costs associated with increasing dollars in TRM. Because TRM does full backprop through all 1+ lost steps in the final cycle, making null larger directly increases the size of the computational graph that needs to be stored.
Right, tracking 7 steps needs more memory than tracking 4 steps.
Exactly. The paper notes that pushing null and much beyond 6 often led to out-of-memory errors on their hardware. So, 166 represented a sweet spot deep enough recursion for high accuracy, but just within the limits imposed by the memory cost of full backpropagation.
HRM avoided that OM limit by using the inaccurate one-step gradient, but paid the price in performance. TRM accepts the memory constraint as necessary for accuracy.
It's a conscious trade-off for rigor.
Okay, let's talk about the adaptive computational time, ACT, again. We know HRM's version was complex and required 2 NFP per training step. How did TRM simplify this?
TRM made a really significant simplification here. They realized that the whole Q-learning part of HRM's ACT, the part that tried to predict the value of continuing versus halting, was likely overkill and was the source of the 2 NFP cost.
Because calculating the value of continuing required that second forward pass to get text-neck.
Exactly. So TRM just removed it. They got rid of the math loss component entirely.
So what's left? How does TRM decide when to halt?
It uses only the simple halt loss. Math calls halt. It still has a halting head that outputs a probability $2, let's just call it $2. And it trains this head using a simple binary cross-entropy loss, comparing tollers to whether the current prediction is correct.
So basically, if my current answer is right, predict halt. If not, predict continue implicitly by predicting low halt probability. That's it.
That's pretty much it. A simple BCE loss on the halting probability based only on the current step's outcome.
And the impact of this simplification, does it still adapt the computation time? And what about the 2 NFP cost?
Yes, it still learns to halt early on easier samples, achieving adaptive time. But because it no longer needs a Kleschenix, it eliminates the need for the second forward pass. The training cost drops from 2 NFP per optimization step back down to 1 NFP.
So TRM trains effectively twice as fast per optimization step compared to HRM, purely due to this ACT simplification.
Correct. And here's the kicker. Did this simplification hurt performance?
Did it?
No. In fact, performance slightly improved. The ablation showed accuracy went from 86.1% using the complex Q-learning ACT up to 87.4% using the simplified BCE-only ACT.
Wow. So the complex machinery for calculating the continue value in HRM's ACT was not only computationally expensive, but actually slightly detrimental to performance. Less complexity led to better results and faster training.
Another win for simplification and rigor. It suggests the original ACT formulation was unnecessarily complex.
Stability must have also been a concern, training these tiny models on just 1,000 examples. Any tricks there?
Yes, this was critical. Training small models on small data sets can be very unstable. Gradients can be noisy, leading to weights jumping around wildly, and performance can suddenly collapse.
How did they combat that?
They relied heavily on exponential moving average, EMA, of the model weights.
EMA, how does that work?
Instead of using the raw model weights directly after each optimizer update, you maintain a separate set of averaged weights. These EMA weights are updated slowly, typically as a weighted average of the previous EMA weights and the current raw weights. Like EMA weights, beta EMA weights plus 1 beta current weights.
With beta being close to 1.
Exactly. They used a high momentum factor, 1 beta 0.9991. This means the EMA weights change very smoothly, averaging out the noisy fluctuations from individual training steps. You then use these smoother EMA weights for evaluation and inference.
And did this make a big difference?
Huge. Table 1 shows that without EMA, accuracy on Sudoku-Extreme plummeted from 87.4% down to 79.9%. That's a massive drop. Email is absolutely essential for stabilizing training and achieving good generalization on the sparse data. It prevents that sharp collapse they mentioned.
Makes sense. Smoothing out the updates helps find a more robust solution. Okay, one last architectural piece. The choice between attention and MLP mixer blocks inside the net module. Why wasn't one architecture universally best?
This finding really underscores that architecture choices are often highly task-dependent, specifically relating to the nature of the input.
They tried replacing the standard self-attention mechanism common in transformers with something else.
Yes, they experimented with using simple multi-layer perceptrons, MLPs, applied across the sequence dimension inspired by the MLP mixer architecture. This is basically an attention-free approach.
Yeah.
It just uses MLPs to mix information across different positions in the input sequence, like the cells in a Sudoku grid.
Why try that? What's the potential benefit?
MLPs are generally simpler and computationally cheaper than self-attention. The hypothesis was that for tasks with a small, fixed input size, like a 9x9 Sudoku grid, where the context length LA on one ball is constant and relatively small, the powerful, dynamic relationship modeling of self-attention might be unnecessary overkill and could even contribute to overfitting.
And did the MLP mixer approach work for Sudoku?
It worked brilliantly. The TRM MLP variant, using MLP mixer-style blocks in the 2-layer net module, totaling only 5M parameters, achieved the top Sudoku-Extreme result of 87.4%.
So for small, fixed grids, simpler is better. Less inductive bias, more reliance on the raw recursive processing.
That seems to be the case. The dense all-to-all mixing of MLPs was sufficient, and removing the complexity of attention helped generalization.
But what about tasks with larger inputs or inputs of varying sizes, like the maze-hard or ARC-AGI benchmarks mentioned?
Here the story completely flipped. For tasks using larger grids up to 30 by 30, so L9 for $100, or where the input size can vary between examples, the MLP mixer approach failed dramatically.
How about?
On maze-hard, TRM MLP scored 0.0% accuracy. Total failure.
0%. Why such a drastic difference?
Because for larger variable context lengths, the inductive biases of self-attention become crucial. Attention's ability to dynamically focus on relevant parts of the input, regardless of their distance, and to handle varying sequence lengths effectively, is essential for generalization on those more complex tasks. The fixed receptive field and lack of dynamic weighting in the MLP mixer just couldn't cope.
So for those harder, larger tasks, they needed to stick with attention.
Yes. The TRMAT variant, which used standard self-attention layers in its net module totaling about 7M parameters, was required. It achieved strong results on maze-hard around 85.3% and the ARC-AGI benchmarks, significantly outperforming the MLP version.
So the optimal internal architecture net depends heavily on the input characteristics, especially context length dollar, MLP for small fixed dollar, attention for large variable dollars.
Exactly. There's no single best block. It's task-dependent.
Okay, let's wrap up the results with the final comparisons. Tables 4 and 5 summarize the performance across the board, comparing optimized TRM against HRM and the big LLMs.
Right. Using the appropriate TRM variant for each task, TRM MLP for Sudoku, TRM AT for maze-arc, the results consistently favored TRM over HRM, despite TRM having 75% fewer parameters.
Give us the highlights for ARC-AGI, the abstract reasoning challenge.
On the first ARC-AGI-1, TRM 7 MBParams achieved 44.6% accuracy compared to HRM's 27 MBParams 40.3%. A solid improvement.
And on the harder ARC-AGI-2, the one where Gemini 2.5 Pro reportedly got only 4.9%.
On ARC-AGI-2, TRM hit 7.8%, while HRM managed 5.0%. So TRM significantly improves over HRM and substantially outperforms the reported LLM baseline on this very difficult task, again, with a tiny fraction of the parameters.
Then Sudoku-Extreme.
That was the most dramatic difference. TRM MLP, 5M params, achieved 87.4%, whereas the best reported HRM result was around 55-60%, depending on exact configuration, a massive gap.
So the conclusion seems clear. TRMs approach architectural simplification, single, 2-layer net, rigorous math, full backprop, optimized recursion, stable training, EMA, And task-specific blocks, ML-potention, allowed these tiny models to punch way above their weight, achieving state-of-the-art results on complex reasoning tasks by focusing on the process rather than just scaling up.
That's the essence of it. Left parameter bloat, more focus on efficient, mathematically sound, iterative refinement. Hashtag now tag outro.
Okay, let's try to pull all these threads together. We've gone through LLM limitations, HRM's complexities and flaws, and TRM's elegant simplifications and rigorous approach. What's the big picture, the main message for you, the listener, to take away from this deep dive?
I think the biggest message is a direct challenge that scaling is all you need. Philosophy, at
Yeah.
least for certain problem domains. TRM provides really compelling evidence that architectural ingenuity and mathematical honesty can be far more impactful than just throwing billions more parameters at a problem.
Yeah, it feels like TRM demonstrates that complexity isn't always better. Sometimes stripping things down, making the core mechanism simpler but correct, is the path forward. Getting rid of the dual networks, simplifying ACT, using fewer layers.
Exactly. But the crucial counterpart to that simplification was the increase in mathematical rigor, specifically around the gradient calculation. Abandoning the flawed IFT shortcut and committing to full backpropagation through the relevant steps seems to be the absolute key to unlocking high performance on these tasks.
Because accurate gradients mean more effective learning, especially when the task requires intricate multi-step reasoning.
Precisely. TRM essentially traded a bit of memory efficiency, compared to HRM shortcut, for a massive gain in gradient accuracy, and that trade-off paid off handsomely in terms of final performance and generalization.
So for hard constrained reasoning problems, maybe the bottleneck isn't the raw knowledge capacity, parameter count, but the model's ability to perform reliable, iterative, step-by-step computation.
That's certainly what this research suggests. Robust, deep recursion, enabled by simple architecture and sound math, seems to be more critical than having a giant memory bank, at least here.
It's a really powerful demonstration of prioritizing the process of reasoning over just the scale of the model.
It really is. But, it also leaves us with a really interesting, maybe provocative question for the future, doesn't it?
Oh, what's that?
Well, TRM success, as impressive as it is currently demonstrated primarily on these supervised learning tasks, puzzles, with specific inputs and known correct outputs. The big question is, can this philosophy, this principle of tiny, efficient, deeply recursive models with rigorous gradients be extended beyond these deterministic puzzles?
You mean, could it apply to the areas where LLMs currently dominate, like generative tasks, creative writing, dialogue, coding assistance?
Exactly. Could we build generative models based on TRM-like principles? Models that perhaps iteratively refine their output using some internal reasoning state, CETL dollars and solution CETL dollar, but applied to open-ended generation rather than closed-form puzzles?
That would be a paradigm shift. Imagine a generative model with the logical consistency of TRM, but the fluency of an LLM, running with maybe tens of millions of parameters instead of hundreds of billions.
It's speculative, of course. Bridging that gap from supervised reasoning to open-ended generation is a huge challenge.
Yeah.
But if the core principle holds that architectural rigor and recursive refinement are keys to intelligence, then exploring less is more in generative AI could be the next major frontier. Maybe tiny recursive models are the path to truly efficient and capable general AI.
That's definitely something to chew on. The idea that the future of AI might be smaller, leaner, and more mathematically honest. A fascinating possibility.
Indeed.
Well, this has been an incredibly insightful look under the hood of these tiny giants. Thank you for breaking down the complexities of HRM and TRM for us.
My pleasure. It's exciting work with potentially big implications.
And thank you, our listener, for joining us on this deep dive. We'll be back soon with another exploration into the cutting edge.